Ook die doet het zo. Ja. Nee, als het goed is ook van voren. Als het goed is, komt hij. Ja, 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 ja. Doet het gewoon. Zacht? Vind je hem zacht? Ja, dat kan wel kloppen, want hij staat hier niet heel erg hard. Zo, dat is denk ik wat beter. Ja, als we die erop zetten, dan hoor je die er wel doorknappen.
Ja.
Ja. Dus, nee, dit gaat wel goed. Nee? Ja. Ja. Ja, dat kan. Dat kan. Ik weet alleen niet waar hier de versterkers zitten. Zo, ha, ja. Of dat je hem daar nog iets terug kan halen. 1, 2, ja, ha, ja, ja. Zo, ha, ja. Kijk, dat doet al wat. Ja, nou prima.
Ja, ik weet niet hoe het er nou hier uitziet.
Nou, hier ziet hij er nou netjes uit.
Yeah, cool, thanks. Perfect. Oh. all about boosting your productivity. Oh, there's the mic. Boosting your productivity at work, giving you more time to spend on code and not making PowerPoint presentations. So what we're looking at here is a Quarto presentation, and that's a tool that we use every single day at work. And yeah, I'm going to show you kind of the end result and then go through how I built this and how easy it is to move from your Julia script into something you can share with your stakeholders or with other interested parties. So I made this one up yesterday. I thought the timing was quite good. A very random data set, which is the England versus Netherlands football match tonight, as I'm English, in the Netherlands. So yeah, it's kind of more about the format of the slides rather than the content. But here's a quick sort of title slide, and you can show you sort of the bullet points going through, all as you would in a PowerPoint presentation, but without the need to directly say, I want this to happen, this to happen. And yeah, quick team comparison. So we've got our sort of like simple text slide. You can put emojis in there, titles. All the transitioning happens automatically. We can load PNGs in there, any images. These are charts which are made kind of on the fly. Colours look a bit off there, but this is a comparison of the last 5 matches between England and Netherlands. You can see the Netherlands are certainly looking a lot better in terms of wins and goals. So not much hope for me tonight. And you'll see here as well, we also have some PNGs which are loaded, so these kind of players to watch are Golden Boy, Jude Bellingham, and the Netherlands Golden Boy, Gakpo, I think might be top scorer at the moment, so worrying. And yeah, my unbiased prediction is the Netherlands will actually win. That's my view. I am a cynic. And you can see here, even in Quarto, we can even have some nice confetti effects. And England to blame the referee. So that's a quick demo of, or quick example of what Quarto can deliver. And we will now have a quick look at how this is actually made. So the beauty of Quarto and literate.jl, which is a package which converts our Julia script here into the markdown format we need to create the Quarto presentation, is that I can work here directly in Julia. So it's the JL script file. I do all my imports as I normally would. A little bit of boilerplate to make sure I'm in the right package, but that's my issue for pushing to certain places. This is just normal Julia code with comments, right? So we see here this is a heading, a level 1 heading, and it's prefixed by the extra hashtag here. A level 2 heading, bullet points are just simple hyphens. We have the rest of our headings, and then just pure Julia code here. So it's the function that I've got, which creates those Mackie.jl plots. We go through there, and there's a bit of boilerplate for Quarto. So this is how I got those charts to come in incrementally as I went through the slides. We have our simple load of our PNGs here, which is just markdown. We have the figure tag, the figure text, and the file path where it saves. You'll see that in my project directory here. These few here. And any kind of bolding, emojis, or anything like that. So the beauty of this is I've got this very straightforward Julia script, and I have some tasks set up. So I have a task here which runs a literate script to convert this into a QMD. So you'll see that here. So you can also create these in pure QMD if you don't want to go from Julia, and you'll see the normal markdown notation. So it's converted this Julia script into this Quarto QMD. And from here, I have another task. This is the beauty of VS Code, is you can set your user tasks. I'll show you those quickly at the end and try and share them as well through pre-talks. We also then have another task, which if I get the right button, it's not that one. It's not that one. Okay, they're not going to work. They would normally give you a preview so you can make changes on the fly. But what I'll do instead is I'll start in here and I'll run a task which is Quarto render. This should start up the Julia process, which it is. So this is now using the current pre-release version of Quarto, which uses the Julia engine, as opposed to needing to worry about iJulia or Jupyter, which is a real nice change. Would recommend downloading it. And you can see here in my terminal, it's just going through and running those code blocks, producing the reports. And there we go, they're done. So it's these two files here. So I have HTML, so these are both done at the same time. This is the HTML report, which is easier. We find it easier if you're, we might do a presentation to business stakeholders, and then afterwards we share it, but it's easier to share as a flat report for them to scroll through, as opposed to having to click through the slides. And from here, we can directly then just go to the Reveal.js version of that and open up our slides here. And the real beauty of this is I can quickly come in and make changes. This might be a report that we have monthly. I can have my data downloading as part of this. So if I, if I had a CSV file, I could just add that in there, load that CSV. Every month I could just come in here, rerun this report, and it would update automatically. So let's say that this stat changes. It would more likely be Netherlands 4 wins, England 1 win still. Quickly reproduce that report. The Julia service is still running from last time, so it's even quicker. And I come back into my slides, and you'll see that that has already then updated, ready to share, ready to present. And yeah, that is, I think, the quickest demo of Quarto you could possibly give. There's so much more to it. There's so much more customization. There's so many more plugins and extensions. And the real beauty of it is I can now work up to 10 minutes before my presentations, quickly hit a task shortcut on my keyboard, and be ready to present. Not ideal. My boss is in the room, so I normally give myself at least a day of prep. Yeah, he knows that's not true. Cool. Thank you, everyone. Any questions quickly? I think we've got a couple of minutes.
Why would you not work through QMD like from the beginning? As you said, it's possible, but why going through the pain of doing JL and then QMD?
I think for me, I quite often work through my analysis kind of just in these raw JL files, work through it interactively, and then it's easier for me to then quickly switch from this. I'll go in, I might have another section here, and I'll have some charts created. I'll have tested those in VS interactively, and then all I've got to do is go, okay, so I want to add a title to this, so new chart, add comments. It kind of exists in that script. And Literate does that so seamlessly that it's easier for me to do it that way. Thank you.
Thanks for the talk. I had a quick question. How good is the LaTeX support?
Very good, actually. I haven't used it a whole lot, but if you check out Quarto, another great thing, really good documentation on Quarto, lots of great examples. But yeah, all supported. Yeah, I can't speak too much to it.
Thanks.
Thanks. Cool, thank you. That's me. Thank you very much, everyone.
Adapter stays here. Okay. Be sure, Bob.
So thank you everyone for being here. Today I want to talk about a package that we wrote not too long ago. I think over this last year we've been working on this package called Inti. So this is working in collaboration with Thomas Anderson, who is a professor at Rice, and Carlos Perez Arancibia, who is a professor at Twente. And my name is Luis. I'm a research scientist in France at this INRIA Institute. So that's why all the logos. Okay, so let me I think this will be a little bit of a technical talk in terms of the math. So I'll try to go maybe not so fast. So Inti is this, like I say, library to solve these things called boundary and volume integral equation methods. So we include sort of high order schemes that's really close to our research. So we hold that it's important for us. We have support for this so-called acceleration methods. We really wanted to be able to handle both academic problems and also sort of big industrial size problems of including complex meshes. There is some documentation, and you can go through the online documentation. Of course, it's not complete like any documentation, but should be fine. Okay, so I guess if I manage, first question is why would you want to solve an integral equation? So there are many PDEs actually. So these are kind of niche methods, but when they apply, they can be very, very useful. So there are many PDEs that can actually be recast in terms of these so-called boundary integral equation methods, okay? And when you can do that, it leads to really highly efficient solvers. So this is an example of a simulation of some sort of acoustic scattering, if you want, of an airplane. 3-dimensional simulation. We've visualized the pressure field across a plane. And these simulations, you can run them, on a decent laptop or like a reasonable desktop if you're sort of using these methods, okay? And I'll try to explain why that is the case. So the second question, why Julia? So yeah, why boundary integral equations? That's what I work on. So why Julia? Well, we found the ecosystem for the scientific and numerical linear algebra to be quite good, actually. It's also very composable, easy to build abstractions, which we will need, because these methods tend to be complicated. We found the syntax to be kind of user-friendly compared to, say, C++. And we really needed the ability to write fast code where it mattered. So in Julia, we found that this kind of, we had everything that we needed in there. So let me just go through an example of what the syntax kind of looks like. So the first line is, I think it highlights composability. So we're actually not going to code lots of the things here, like iterative solvers, we're not going to code them. Or these H matrices is some sort of way of compressing some big dense matrices, okay? There's the gmesh.jl package that allows us to handle meshes, to visualize things. So the first line is, I think, a good showcase of how Julia allows for this type of composability. So kind of standard when you're solving these, say, physics-driven problems, you have some sort of representation of your geometry, you have to mesh it, way focus on the solver, of course, and then you have to post-process, maybe using Mackie, maybe using some paraview, you export a paraview file, so that's kind of up to you. So the usual stuff, you import a mesh, this is a gmesh file, so if you're not familiar, it's just a mesher. Then you sort of extract what is your domain omega, so the interior of this sphere. Then you have to look at the boundary, you have to build some sort of quadratures, and these are sort of the main focus of the package, and I'll try to explain a little bit of the method behind it, because it may not be so clear to everyone, what are these single double layer objects. And then you can kind of just call an iterative solvers, you build some linear map, so these objects are actually, you can just lazily compose them, mostly thanks to linear maps, so we just build on top of that. And you can solve, say, a scattering of a sphere, so in this case it's a bit simpler than the airplane. But this one runs maybe in about 5 minutes, so it's a 3D, relatively, not high frequency, but not super low frequency either. So I think that's sort of an example. So now I'll sort of try to convince you in the first section why these type of methods are perhaps interesting for some applications. Then we take a sort of quick look at the main structure of Inti, the high-level API, and how we build these things. Then we go through some documentation, examples, roadmap, conclusions, and let's get going. So in a bit more detail, what I said earlier is that usually for many PDEs you recast them as these integral equations. Examples that I just show here, so Laplace, Stokes, Maxwell, you can do elastostatics, elastodynamics, so as long as they're linear piecewise constant coefficients, let's say the methods are useful. So the main advantage is actually that you just pose your problem on the boundary of your domain. So that's why you have less degrees of freedom, and that's why you usually can hope to be more efficient. So if you're in 2D, if you imagine in 2D, instead of having to have n by n degrees of freedom for a square, you just have n, or for n for the sides of the square. Okay, so you can sort of hope for this linear, quasi-linear complexity, where linear means in terms of the number of degrees of freedom of your boundary. Now, of course, that comes. So the main advantage I would say is this one, and then there are sort of more technical advantages that you actually exactly solve the PDE, so you don't have these errors called dispersion errors. So what you construct is an exact solution. The drawbacks, of course, there has to be some drawbacks, is that yes, you have n by n systems, but they're dense. So these are dense matrix. So if you're just trying to store them in memory like that, or do operations with them, factorize them, that would cost too much. And the second difficulty is that actually the operators you're going to write have some singularities that you have to handle. And I think this is sort of one of the main reasons why we don't see these methods too often used in the wild, even when they are probably one of the best choices of methods that you could use for those problems. So they're not applicable to many PDEs. So this is by no means a competition to like finite element methods. It's just for some PDEs, it's an alternative. Okay. So I think this is sort of the drawback that we observe, and we do research in that, and we thought it would be nice to try to take a step closer to people who actually want to solve some PDEs. So let me be more concrete and show through a simple example how do this type of methods work. So suppose very simple problem. You want to solve a Poisson problem with Dirichlet boundary conditions. So omega is your domain, and the notation will be that gamma is just the boundary. Okay. So the usual thing that you can do is you can just first build a particular solution. So that means that it solves with the f right-hand side there, but it doesn't satisfy any sort of boundary condition. So that's just a convolution of some sort of special function. So this is the Green's function. And I wrote here where it is for Laplace 3D. So it's kind of Newtonian potential type of things. And the important thing to notice is that this function is actually singular when x equals to y. So that's one of the difficulties I mentioned. And the second one is this function is never 0 for x and y. Okay, so that's the dense matrix. So dense, this function doesn't vanish. Interactions arbitrarily far apart. Well, it decays, but quite slowly. Okay, like 1 over r. And the second one, it's singular, so integrating these, you can imagine like standard quadrature rules are going to have a problem. So coding this gets a bit tricky, let's say. So the first part, you sort of build this particular solution, and then it doesn't satisfy the boundary condition. Then you have to come and sort of correct with what is called a layer potential to take into account the boundary condition. And this sigma is some layer density, so this comes from physics. It's a single layers, where people kind of put monopoles. You can conceptually think about putting monopoles on your boundary. Okay. Now this is only integrating over gamma. So once you do that, you actually construct a solution to the PDE without, say, only having these integral operators. Now this was Laplace, and you can more or less generalize these to L. L has to have some properties like strongly elliptic systems, things that would be fine. You can generalize boundary conditions. This is like a Dirichlet and a Neumann boundary condition. So you can more or less do this for like a wide class of problems, but you keep on running into this type of objects, so volume potentials, which are integrals over your whole domain, and then boundary potentials, which are integrals over your boundary, of the singular functions or derivatives of those singular functions. Okay? So not really important, the notation here is just to say that we more or less understand what are the building blocks for these inter-equation methods, and they are really built around these 5 integral operators that I wrote here. And the purpose of the package is really to provide you a way to accurately and sort of quickly evaluate these things. So you see these are sort of non-trivial tasks because accuracy, you have the singularities, and quickly you have the dense matrices. So you have to do something with it, otherwise these methods are not practical actually. So let me just go take one word on the discretization schemes, since it's not probably not a very well-known method. So suppose I want to solve for u in an equation of this type. So I have I don't know u, I'm given f, I'm trying to find a u that solves this inter-equation d some domain. It could be omega c or just the boundary. Well, what we'll do is we just approximate this integral by some quadrature rule, not saying how you build that, but you have some way of integrating over this domain d, and then you just replace the integral by a sum, okay? And once you do that, you have to sort of figure out how do you compute the values of u at the unknown at these quadrature nodes. And you can, these type of methods that we implement, they will just impose a strong equality at the quadrature nodes, and then you solve the resulting linear system. So now this is just a linear system, which is identity plus some dense matrix equals to f. Okay, once you solve it, you have your solution essentially. And this is what is typically called an instrument discretization scheme. So I'll come back to the challenges and to sort of, I think this explains a bit of the structure of the package. So I'm not going too much into the usage of the package. I think the documentations are for that. I'm trying to give the sort of the conceptual design here. So we need to approximate objects of this type, okay? And these approximations need to be efficient and accurate. And typically what is done in the community is that, well, you have this sort of sums of lots of, so this is conceptually a dense matrix, and there are methods that actually can compute these sums quickly. Okay, so examples of these methods are the fast multiple method, hierarchical matrices, and there are several others. So everything in blue is implemented in INTI right now. And then these quadrature rules here, which are just sort of a standard naive quadrature rules for integrating, say, polynomials. They are not accurate near the diagonal of the matrix, just to make it simple. And then you have to come and sort of correct with a sparse matrix. Okay, so this other object looks like a sparse matrix. And this is what I'm saying here. Typically, the cardinality of the correction points is much smaller than the degrees of freedom. And this is really the central design. We want to be able to plug in different types of acceleration, different type of corrections, okay, because in some applications, you're better off doing one or the other. So what are acceleration methods? They're just sort of very clever algorithms, usually tree-based algorithms, for computing sums of this type for some sort of well-known kernels. They rely on some analytic properties of these kernels. The important point is that they're able to compute these sums. So you evaluate this matrix, which is conceptually an m by n matrix, and you can multiply by a vector in something which is linear or log linear, the size of the matrix. Okay, so it's kind of, if you want FFT, would be something that does that too. But this doesn't have the structure of FFT. Okay, so there are some other methods. The input. So I think this part of the code is kind of very well established. The input for this type of accelerations, you have to tell me what's your function, where do you want to evaluate it, where do you have your source points, you know, and what are the source strengths. And then just output the values of these sums. And from a software point of view, this was actually relatively easy to get right, I think, in the library, because the interface is very clear. We didn't code most of the methods I mentioned, we didn't just code them, but there are wrappers available, there are Julia wrappers available, and if they're not, we can always write one. So this was, to get it right, we just hook into existing code. We don't want to reinvent the wheel, actually. So that was relatively fine. And this is very crucial for the performance, because if I deal with dense matrices, I mean, forget about it in terms of memory and in terms of efficiency. So we cannot redo that. The methods lose all sort of practical interest. And the corrections, on the other hand, they're kind of this difficult to state object that I write on the right here that sort of says, well, you have your integral, and you want to approximate it by some sum of a standard quadrature, but then it's not always quite right, and you have to correct for it, okay? And these are, I think, very difficult to state the method here. I won't try, okay? This is really the several methods that you can try. Usually they output some sort of sparse matrix. You can at least reinterpret them like that. The approximation properties are difficult to state. All you hope is that this, with this term, is better than without it, okay? So the approximation is improved in some sense. The many method available, usually there's no software that goes with it, so we had to code it. And I think from a software point of view, I think this is sort of the ugly part of the library. Every method gets its own kind of interface. Like you have to read the doc of the method to decide. Okay, so there's some reasonable defaults, but yeah, this part is something that requires, I think, a bit further work to define what we really mean by these corrections first, and then maybe try to implement the generic interface for all of them. And this is, of course, crucial for the accuracy. So, I mean, getting solutions quickly is important, but they better also be right, otherwise it's not very useless. It's not very useful, okay? So, yeah, the main goal is really to be able to compose. What we wanted is that you should be able to switch between different methods easily. We want to be able to compose these operators, so I showed very simple examples, but the moment you start to mix boundary conditions and different PDEs, you have some elasticity problem coupled to acoustics, okay, then you may need to start composing these objects. We want to handle complex geometries, and we want to do so efficiently. So that led us to try and decide and write a package. Okay, so that was it with the sort of mathematical preliminaries, and now we hopefully have an idea of what these objects are, single, double layer. So there is a very high-level API, which is really designed around most of the problems we solve in our in practice in our research, which are sort of PDEs, you know, relatively simple PDEs, I should probably say. So the API, the very high level, really revolves around building these 5 integral operators I mentioned. So single, double layer. The others have a different name. Doesn't matter what they are, but you can always build them, and they kind of look the same. You have to say where do you want to evaluate it, where do you integrate over, what's your PDE. You know, this PDE comes with some parameters. So if you're doing Maxwell, if you're doing Stokes, you know, the keywords would be different. And then these 2 parts over here, which is what we really wanted. We wanted to be able to switch on and off a fast multiple, exchange it for maybe a hierarchical matrix approximation. So that's the joint double layer, and you know, we use a different correction here, for example, and you have some sort of parameters for these corrections. And then just the volume potential, which is, I mean, very much, I mean, I guess if you see from far away, they all look the same. Internally, volume potentials are different than these boundary integrals, but not. Okay, so currently we support these PDEs. I think they're fully supported, meaning they have acceleration corrections in 2D, 3D. But then I guess I could always just wrap very ugly code into that API, and it wouldn't be a very composable library. So what do you do if you actually don't have one of these PDEs? You have your own kernel, you somehow had your PDE that you found a fundamental solution, and you want to use the library? Well, so almost everything in the library, that's probably, no, it's not the first slide we'd call the show, but almost everything in the library revolves around this object, which is the integral operator object. Kind of makes sense from what I've been talking about. This is our central object, and this is the central structure of the package. And at the high-level API, all it does is just actually provide some syntactic sugar for, you give me the PDE, and I know what the Green's function is, because I hard-coded it for you. I mean, I looked up some old book and found very ugly expressions for some of these. And then I pick an acceleration method. So there are several functions inside, like assemble H matrix, assemble FMM, that take some parameters, and I try to make them more or less uniform for the user. Then I pick a correction method for you. So how do you compute this accuracy? So these sparse matrices that are intended to improve the accuracy of your method. And then I just sort of wrap everything around. Maybe I wrap it around a linear map if I can't really have a good direct solver for you. Maybe I wrap it in some other object that would allow you to do an LU factorization. Okay, so depending on the acceleration methods that you ask, you may actually have no matrix whatsoever. Okay, so there's no full algebra that you can do with these objects. All you can do is just multiply by a vector. And then you're sort of forced to have an iterative solver. So that's all that we do. So if I suppose that you have some kernel that is not one of the ones I coded, so just take a simple one, which is, yeah, so this is, it's called directly Green function, but you just have some custom kernel if you want. Well, you have to define your own kernel here. So this is just showing you have some function that takes a target and a source, and there is a parameter for this one, which is k. And then, well, this is just boilerplate because I need to create the mesh and the quadrature and all of that. So we have a kind of, for simple surfaces, simple curves and surfaces, we have kind of an internal representation of geometries, which you can just write what your curve is if you want, and yeah, and then we'll handle the meshing for simple problems that works. Actually, for most of our research papers, this is enough. And then at the end, you actually instantiate this integral operator, okay? And then after you have the integral operator, you have to do these 2 parts. You split it into 2 parts: the dense part, which you compress, and the sparse part, which you correct. And this is an example of if you call. So this is what the API does. We're just doing it directly. You call this assemble H matrix, and this creates this hierarchical matrix object, which, as you can see, is a 3-data structure. Okay, it has some leaves, it has some dense blocks, some sparse blocks, some data sparse blocks, and this is sort of giving you some information of how much did you compress this full matrix actually. And then the second step, like we said, is that I had this sort of S0, but it wasn't a very good approximation to my operator. So I have to build some correction. And we see here that the correction is just returning a sort of simple sparse matrix structure. So, okay, so there's some code that will hopefully give you high order conversions and give you accurate approximations. And then after you're done with that, you can just combine them. How do you combine them? Well, you can maybe just wrap them in linear maps and use an iterative solver after that. So with that, you could essentially have your own kernel and plug in. And I know this is not it's not like at a console level, but it's difficult to. I mean, I think it's difficult to go all the way to the just PDE and boundary conditions, because I think at least for now would lose too much of the flexibility that we want to have. So you have this modular way of assembling these generic integral operators, but you still have to do some of the lifting. Like you still have to understand how these methods work, reformulate your problem as a boundary or volume integral operator problem. Okay, so it's not a, at least for now. I mean, at least for now, it's not a, it's not given. Right. So, but you do have this modular way that you can create things. So conversions are things that we care quite a lot about because we do a lot of work to have these corrections, to have them be high order, to have the methods be accurate, so that you have, for example, fewer degrees of freedom. And I guess one thing that I found a bit difficult is how do I check that my methods stay high order? So I have, of course, we have unit tests, but it's really hard to sort of track convergence rates. Like, is this, I mean, when we published the paper, this was a high order method, we have the figure, we showed it, and then we tweaked things here and there. Did I break the convergence rate or not? So it's something that we are, for now, so it's really difficult to unit test these things. The solution we have for now is there is sort of a separate dedicated repository that with every tag, we run some sort of convergence tests, okay? So this is sort of classic convergence stuff. We expect, say, a fifth order convergence of this method as it goes to 0. This takes some time to run, okay? So we don't run them on every commit, for example. But still, a human has to sort of come and look at this and say, yeah, you probably didn't break it. Okay, maybe we could compare images to some saved versions of these images, but we don't do that yet. So I think this is all auto-generated. So it's actually just a package that generates a documentation that puts these figures in, okay? And I think we still have a lot of work to do. I'll be sort of happy to see how people track high-order methods and make sure that they don't break as the code evolves. So for performance considerations, I've been sort of saying that we want to be performant. So most of our performance is actually derived from libraries that we didn't necessarily write. We actually just wrapped some of these fast multiple libraries, for example. Okay, so you do have the choice, and some problems will be better with one tool than the other. We do efficiently implement these sort of correction methods that we have. The runtime overall appears competitive with other things that we had in our research, so old code written in Fortran or things like that. But I think there's still, of course, much work to be done, and it's by no means complete. Okay, we don't have a automated way for now to track performance regressions. I know there are packages for that, but we just didn't do the work required. And now, I think just to show what the documentation looks like, maybe some examples. I won't do a live demo, but so there are the first sort of, this is really scattering 101. This is the prototype of a problem where integral equations are probably the best tool you can find out there. So you have some Helmholtz equations, so this is time harmonic acoustics, and you have some obstacle, so a ball or something, and you have a wave, say a plane wave coming into this, and it hits the obstacle, it diffracts it, it reflects, it does all sorts of things. And I think I need to, so this is what the documentation, apologize for this. Maybe I should have done this full screen like that. Okay, so we have some examples. Someone mentioned, I think, literate before. And so the examples in this package, they are sort of auto-generated using literate. So this is an example of, there's just a JL file somewhere that gets converted into this markdown with the documented syntax, and then there is some Jupyter notebooks that one can read. And that's sort of an example of how you'd solve this in real life. And when you may actually want to not, because of flexibility, you may not want to mesh things by hand. You may just want to use a mesher. So this is composing with this gmesh.jl. So you could create possibly very complicated meshes. This would mesh your surface, and then probably just solve a scattering problem or move a bit. I think we're just trying to compare to exact solutions, so that's why the example is a bit long. There are some exact solutions that you can figure out for simple geometry, so just to have an idea of what are the errors that we are committing. So yeah, so you can solve scatters in 2D. You could have more complicated objects. I mean, these are still very simple, but so that the documentation, and of course you can do it in 3D as well. It's just a matter of changing one parameter, one keyword, and of course be more patient with the time that would take. Okay, of course this is not going to be at the same speed 2D or 3D. So that's kind of the Helmholtz example that I showed. And then the second one is this Poisson problem that I explained at the very beginning. Yeah. So for the Poisson problem, yeah, I'll probably not go too much into detail because I do want to take some questions. It's very similar in nature. I already explained what we do of building a particular solution and a homogeneous solution to the problem. And then there are all these geometry meshes. I think it's a quite flexible mesh data structure that we have because we need conformal meshes. So for these high order methods, you better actually also mesh the boundary to high order. Otherwise, it's not really interesting to have a high order. I mean, maybe, but for the scattering, having at least a P2 or P3, so at least a curved mesh is important. So we can handle these curved meshes. We can also handle conformal meshes and things like that. So yeah, you build these integral operators. There are some GMRS going on in there, and you can just at the end again sort of compare the error, and it's usually pretty accurate. These methods tend to be pretty accurate when they work. Okay, so with that, I just want to probably to wrap up. So this is a more technical example that I'm not going to go into in the sake of time. So roadmap and conclusions. We released the sort of version 0.1 a couple weeks ago. 0.2, we're working on it. I mean, there's some new methods that we have developed that we want to put in. Okay, new methods that we have recently published that we want to put in there. We kind of want to finalize this infrastructure for automated tests. Of course, we should be tracking performance, otherwise we have a big risk of regressions. There should always be more examples. This is not so clear. I mean, should we really take a step even further and try to say, just give me the PD and the boundary conditions, and I'll pick a formulation for you? I don't feel very comfortable picking a formulation for you just because it's really problem dependent, but maybe we should. That way we get users who don't know any of these objects that I mentioned. And of course, we're looking for community feedback. I think that's why we decided to come and give a talk here. Yeah, so with that, I'd just like to thank you and take a couple of questions this time.
Two quick questions.
Sure.
Firstly, do you support also Neumann boundary conditions?
Yes.
Okay.
Definitely.
And is it possible to connect INTI with differential equations to solve evolution equations or evolutionary equations?
Like DFQ or like DFQ, for example? It should be possible. I think it would require some understanding of how the library works, but I think it can be used as just a black box, like give me the boundary conditions, I give you what the solution is. So there's no, so when you ask if we support Neumann boundary conditions, we do, but it's just because the whole theory of inter-equation supports it. So you can always reformulate even Neumann boundary conditions, even more complicated Robin or so yeah, that's why I say we support it, but yeah. There is a problem here where I think we do Neumann boundary condition in the documentation.
How general is your support for like various quadrature methods? Like if I were to throw some, I don't know, some like sparse grid or small yak type thing onto it, would that also fit into the API?
Yeah, so it wouldn't fit into the highest level API, which actually just asks for a quadrature order. So if I go through maybe basic usage here, the highest level thing just asks for, when I create a quadrature order. So behind the scenes, what's happened is that we have sort of a bunch of quadrature rules. Actually, that's very close to what we need for the singular integrals. So they're very specialized quadrature rules, and given a quadrature order, we pick what we think is kind of a best quadrature for you. But if you have your own preferred quadrature rule, it fits into like let's say the mid-level API. Like you wouldn't have to go really deep into the code. But when you construct this object over here, you just have to pass your quadrature rule specifically instead of an order. And of course, that has to adhere to certain interface.
Hello, thank you for the presentation. This might be a very dumb question, but I'm going to ask you anyway. I saw that you managed to solve the Helmholtz equation. Would you be able to apply the same methodology to solve a time domain wave equation instead of a frequency domain?
So you can do what they call retarded potentials to solve time domain using inter-equations. We don't support that. So the other way, No. So this package, I guess the short answer would be no, not directly.
Right.
You have to use something called convolution quadrature methods, for example. So there are methods that are going to recast the time, so the time-dependent wave equation, into a sequence of time harmonic wave equations. Then you can do essentially an FFT to go back to time.
So
But
what
yeah.
is the name of the thing that you said?
It's a convolution quadrature.
Convolution
Usually
quadrature.
CQM, so convolution quadrature method.
All right.
It's, I think, one of the most popular ones, actually.
I have another question. Would you
Yep.
be able to describe a function that, for instance, it has a Dirac delta, for instance, a singular point in space or something like that? Would you be able to express that through the package?
I didn't understand the question, sorry.
For instance, like if I have a function that is just like a value in a singular point in time in space, for instance, like is 0 everywhere or 10 in x equal 10 and y equal 10, would you be able to express functions like that that are impulsive with the package? No, right?
So is the solution that behavior? Is it what the solution
No,
wants,
the
or-
solution. For instance, a source term or something like that. I don't know the expression because I solve partial differential equations, not integral equations. I'm not too sure about it. We can talk later. Don't
Sure,
worry.
yeah,
about
that'll be.
it. Yeah. Thank you.
Thank you.
For next speaker. Yeah?
Now we good? All right, awesome. Hey, good morning, everyone. My name is Sam Berklin. I'm a scientific software developer. I offer services through G2I Computing. I've built a lot of simulation and optimization systems in Julia, and today I want to talk about, I think, probably the most useful tool I found for building like robust systems in Julia that I feel comfortable using it and like believing that they're not gonna crash. And just for reference for anyone who might be watching this online or might be watching this later, I do have the slides available up on my GitHub, github.com/samsberklin, and then interface design JuliaCon 2024, in case the code in here isn't very visible for everyone. So to start off, I want to look at something that, like, even if you're not necessarily familiar with quantum mechanics, this might be a script that looks familiar. So we're importing a solver here called Sam's Funky Solver. We're importing a problem type, the infinite square well, and some sort of analytic solver object for this as well. We instantiate an instance of this problem, we instantiate an instance of the solver, and we pass it off to some solve problem function, which returns a solution. The solution in this case is like the first 4 eigenmodes of the infinite square well. So this is all good. But what if we don't want to solve the infinite square well? What if we have some other solver that we're trying to pass into the system? So a first pass at trying to implement a new problem type or a new solver might be, well, I'll just make the types, I'll pass them in, and I'll see where it fails. I think this is not uncommon way to do software development in Julia. I find this to be a really frustrating experience, and it leads to perhaps my most disliked error to run into in Julia, which is a method error, where you try to call a function and you get method error. That's not found. This isn't defined. And I find that to be just absolutely like frustrating to try to deal with, and it feels like there should be a better way of trying to solve that. So yeah, here you run into like there's a field missing or there's like a method not defined for your types. So let's pull apart that like solve problem function that we're calling to try and actually like generate a solution and see what's going on inside. I would say there are a couple things that I would change about this. One is they were hard coding the required fields. I think that we're being very prescriptive then about how people using the code need to represent their problem, which might not be the best kind of solution. We also have like a very specific type signature that needs to be implemented, but this isn't really like written down anywhere. So kind of unless you want to pull open the code and look at this function, or you want to do this like error-driven development kind of approach, there's no real good way of knowing like how do I implement like a new solver type? How do I implement a new problem? So what are some things we could do better to sort of like refactor this and make it a little bit easier for developers? The first thing would be we should obviously add a doc string. Like solve problem is a user-facing function. It's kind of the full entry point for this entire thing. So like we should tell people what's going on there. We should say, these are the assumptions going in, these are the assumptions coming out. The other thing we can do is we can kind of standardize the problem type. So here I've said that whatever problem gets passed in, we need to define a constructor for a problem spec where we're able to convert whatever problem type we're working on into this standard form of a problem spec. And then this feeds into this third part where we have like a very nice solve function or solve method that we're able to implement for our specific solver over this generic representation of the problem to solve, which is a problem spec. So this goes a long way towards documenting like what do you need to do if someone wants to pull open the code and look at what's going on. But it still doesn't get you all the way there. There are lots of questions you could have about like, is this really good enough? So like a big thing is like if you're implementing a new solver type, let's say, you'd want to know like, is there anything else that's going on that I might have missed? And that's a really easy thing to miss. Like maybe there's something nested deep in the code that there's an assumption made there that needs to be implemented. If you're like a downstream user, you might be worrying like, oh, there's a new release of Sam's Funky Solver. Is my code going to continue to work with it? Do I need to like update my solver version or anything like that? And likewise, if you're the developer of the core package, you want to know like, are these changes that I'm making a breaking release? Is this something that like I need to like signal to users that this is a big change and you need to like pay attention and rework your code because things aren't likely to work anymore. So there are some tools that we have available in Julia to actually try and do this better. And the main one that I want to talk about here is being rigorous and formal about our interfaces. This isn't something that we have a construct in the language for, but it is something that we can start to build up kind of ad hoc tests in the test suite that allows us to have some confidence about like, yes, you have entirely implemented this interface, or no, you haven't implemented this interface, and this is what you're missing. So building towards this kind of thing, where we have a test we're able to run that says, you have partially implemented this interface, but here's this one specific method that you're missing, that's where we really want to end up at the end of this. But before we get into like how would we do that in Julia, let's talk about what I would kind of like think about an interface, like what it is. So an interface is really just like, it's a set of methods that need to be implemented. The way that we identify these methods is through like the very specific signature that they need to implement or that they need to possess. Usually that would involve like whatever type you're trying to implement this for, like your new solver or your new problem. And not like inherent to the interface itself, but really we want to get something out of implementing this interface. There should be some sort of higher order behavior that we get out of satisfying this interface. Otherwise, like really what's the point of having this interface in the first place? So I'll look at this code again in a little bit, but really there's like a block that says, this is how you implement that interface. There's a block where we implement that interface, where here the method signature, we put like our new solver type, the shooting method in sort of the first argument, the second argument's that like generic problem spec. And then the higher order behavior that we get out of this would be that sort of like high level solve problem function that we're able to just like pass our solver into and have it work with whatever problem type, assuming that it successfully converts into this like generic problem spec. So I think a reasonable response to have to all of this is like, that's just abstraction. I've been doing this all along. And the answer is yes, you probably have been doing this all along. But I think it's important to take a moment to reflect on like what the abstraction is and how we're thinking about this. Because I think in Julia, and especially people coming from like Python where it's like very class-based, object-oriented, we're very fixated on like structs and data representations. I don't think there's as much care given to methods and what the verbs are that actually constitute the system that we're building. So when we're trying to build with interfaces, like the types are important, the data representation is important, but we want to think a little more abstractly about what are the verbs, what are the actions, like what is actually going on inside of my system. And then like I want to formalize what are the assumptions that I make going into like this interface, what are the assumptions that I make going out of that, and that's sort of like the contract that anyone who implements this interface has to obey. And so one way sort of graphically of thinking about this is this like classic like photo from the internet of how do you draw an owl? Well, the first step is you draw a couple of circles, and then the second step is you draw the rest of the owl. That is a little bit reductive in how you draw owls, but I think that it's kind of the ethos of what we're trying to get at here, where an interface would be one of these circles that we just need to fill in, and then the higher order logic that we get out would be like the full owl at the end. So we want to try to reduce things into like, I build a system out of these interfaces. I don't really know what happens inside of that interface, but so long as you satisfy the contract, so long as like this top circle looks like an owl head, so long as like the larger circle looks like an owl body, I should be able to compose them and get something out that looks functionally like an owl, or I should be able to like get a system out that does what I expect it to do. So this is reorganized a little bit to make the code larger. It's a little bit differently organized on the slides online. But this is revisiting that code where we sort of define an interface. And this isn't drawn from any particular package, but it is sort of generic to how a lot of the interface definition tools we'll talk about will work. There's this bit where you specify what the interface is. This is this like top left block where we have @implement, and we specify this is the interface, and then we specify this is the method. Sort of like a common way of representing where your type that you're implementing this interface for is just like an underscore, like a slot. That's where your type goes. Then we define our struct. We have some way of assigning the interface to our struct. This can be something that's done explicitly. It can be kind of ad hoc. We'll talk about that in a little bit. And then we implement the method. That's just like writing the code exactly as you always would, where we implement the solve method where our type slots into the first argument. And then what we want to get out of this is we want to have some function that we can run inside of our test suite that actually tells us, yes, you have implemented this method. No, you have not implemented this method. Go back and do that, and then like try running the test suite again. So this is what we really want to get out, is we want to have something that can test to tell us that, yes, the interface is satisfied. And this helps cut down dramatically on just like method errors because you forgot to do something. So before we go into tools for solving this in Julia, I think it is worth understanding how other languages solve this to sort of have some motivation. So Rust actually follows a very similar approach, at least syntactically, to how we would do this in Julia, where in Rust we have trait and impl blocks. Trait blocks would be sort of like the interface definition. Here I have like an abstract solver backend trait. Inside of that I say you have to implement this solve function. And then I have an impl block for the abstract solver backend and my type, and I implement the specific function required for that trait inside of that block. And then the Rust, being a static language, is able to then like verify, yes, you have implemented the interface. It like satisfies all the type level constraints that we've placed on it. So this is really nice. This is sort of how we want to think of how I tend to think about them in Julia, but it's a little stricter than we really want in Julia. What with this being a static language in Julia being a dynamic language, and I think that is something that's a strength of Julia. On the flip side, Python does this sort of inheritance through what are called abstract base classes. So you're able to define sort of an abstract class, analogous to like an abstract type in Julia. You're able to assign abstract methods to that abstract class. And then when you implement a class that inherits from this abstract class, you have to implement all of these abstract methods inside of your like concrete class. And then if you don't, Python refuses to let you actually instantiate a method, an instance of that class. So this is nice because we can get sort of multiple inheritance by inheriting from multiple abstract base classes. But it's not great from the Julia perspective because we're not able to sort of like assign interfaces to types after they've been defined. So I don't think we really necessarily want to follow like a Python style approach here either, where things need to be, interfaces need to be assigned at like type definition. So when it comes to actually defining interfaces in Julia, the tools for verifying interfaces are really just like looking at the method table and seeing, at the simplest level, they're just like looking at the method table and seeing if a method exists. This is something that's actually relatively easy to write yourself, but there are tools for trying to automate this process, to automate building these like implementation testing functions for you. Required interfaces.jl is one of those from Sukera or Valentine. It's just like a nice interface definition package. It plays well with supposition.jl, which is a property-based testing package that he's also implemented. Interfaces.jl is another interface definition package. This one's from Raphael Schouten. He actually has a talk at about this package later this week. I'm not sure what day it is, but that would be worth checking out. And both of these packages give you, like, here's the interface definition, here's a testing function that you can run in your test suite. And then finally, a lot of the trait implementation packages that we have in Julia actually overlap with this kind of interface definition problem as well. Binary traits is the one I'm most familiar with. It's kind of in a broken state since Julia 1.10, but a lot of these trait packages do sort of the same thing, where they are either explicitly or implicitly defining an interface. So I think it's worth looking through, I don't know, interface and trait definition packages to see if any of them give you something that might solve the problem that you're working on. A quick note on how we would differentiate interfaces versus traits in Julia. Traits are really just a way of sort of hacking multiple inheritance into the Julia language. And as a consequence of that, we usually think about traits as kind of like a dispatch tool. And usually they're implemented using like the holy traits pattern, where we end up dispatching to like another function with a trait slotted in. This isn't necessarily a way of implementing interfaces, but they may assume some sort of interface internally. On the flip side, interfaces are really like, they're just a collection of methods that need to be implemented. That's really it. There's like not that much more to it at like a fundamental level. Interfaces aren't a dispatchable construct like they would be with traits, but the way that we assign interfaces to types can be kind of dispatchable. Like interface inheritance or like application of an interface to a type could be something that's sort of ad hoc, where it's like, oh, you just have these methods implemented, you implemented the interface. It could be something that's very like based on the typical Julia type hierarchy, where you have an abstract type and then you sort of implicitly inherit an interface from that. Or it could be, you know, this sort of trait-based multiple inheritance approach, where we are explicitly assigning interfaces and they don't correspond to anything necessarily in the traditional Julia type hierarchy. So with all this talk about interfaces, is this actually something that like is used? Is this something that like actually crops up? And the answer is that yes, it's all over the place. So like tables.jl is just like the tables interface. CSV.jl, writing CSV files, anything that implements the tables interface can be written to a CSV using CSV.jl. File path space is a fantastic interface package that defines what it means to be like a file path object, so you can do things like treat remote data and data on your local machine basically the same, and you're able to copy and remove and move data around without needing to think about, does this live on S3 or does this live on my local machine? Pretty much all of SciML is built around an interface, which is why the integration there is so clean, is that everything has this common language of like the SciML interface that everything sort of flows through. One that people are probably really familiar with is the abstract array interface. People are really fond of the array types in Julia, and there's a lot that you get out of implementing that interface. Anything in your code that you've ever attempted to mock so that you can try to test without needing to go through like a full implementation, there's probably either an explicit or implicit interface available there. And at a really fundamental level, like for loops in Julia, just like for x in y, do whatever, that's built on top of the iteration interface. So you just have to implement base.iterate and then you can loop over things. This is sort of a fundamental interface in the language. So I've talked a lot about interfaces, but there are some like concrete advantages that you get out of it from like a software design perspective. It lets you implement testing functions really, really easily. Some of these are more automated. If you use like the interface definition packages, these give you implementation testers. These are essentially just checking, do the methods exist? Maybe with a little bit of extra, like checking that like they're type stable on top of that. But once you've formalized what these interface definitions are, you're also able to start hopefully doing more property-based testing on generic types that satisfy that interface. So you should be able to say, I pass this in, I pass that in, and I should get something that is bounded out or something like that. So you're able to now hopefully do more like property-based testing now that the problem is much more constrained. Being able to then run these testers, which are much more local over just an interface, helps you to catch errors earlier and fail much faster in your test suite, rather than needing to run in it, like the entire test suite to get to the part where you use your new type and find out that, oh, I actually forgot to implement this method, or, oh, I forgot that like this number needs to be like positive when it's passed out. And just by nature of sort of constraining this problem, constraining these interfaces, it makes it much easier to mock these interfaces and then use these mock types in your system to test like higher order logic in your system as well. Because we've essentially tried to reduce the interface down to this contract between inputs and outputs. So if we can mock those inputs and outputs, then we can test that the rest of the system works roughly correctly on top of that as well, which can be much faster than trying to run with like a true implementation of one of these interfaces. There's also just like practical advantages to this as well. Like it does a really good job of defining boundaries for where new code lives. These are those like circles and how you draw an owl. If you want to implement a new solver, it's just like fill in this circle. Like you don't have to, ideally you shouldn't have to think about like how does this interact with the rest of the system. It should just be satisfy the interface and go from there. This should limit where logical errors can occur as well, because if we're rigorous about trying to enforce the contracts on these interfaces, then you're able to start going to like, is the are the invariants satisfied at the input to this interface? Are they satisfied at the output? And kind of speed up your sort of bisection to try to find the root cause of an error. And honestly, it's just really nice to work with interfaces and get kind of a common language or a common verbiage that you use to think about problems and to work about problems, where yeah, you're just like using the same terminology throughout all of your code, and you can have really expressive interfaces that capture pretty much everything and build like really complex systems on top of these very fundamental ideas. So the title of the talk is Building Confidently. I want to elaborate on what I mean by building confidently. I mean that I don't worry that I'm going to run into method errors in production when this stuff is running like hundreds or thousands of times a day, or I have a simulation that's running for like a week. I want to know that I'm not going to accidentally run into a method error like halfway through that simulation and have to restart it. And this is something that's really easy to run into in Julia, because we get this like combinatorial explosion with the composition of types that we try to use with Julia and the multiple dispatch. Like it's really hard to have exhaustive tests. So I don't think that it's tractable to try. I don't think it's tractable to try to check every possible case of every possible type that could be passed in. Really, we want to try to just enforce these invariants at like these interface boundaries instead. And so again, this helps to isolate where like errors can occur. This helps you to test correctness a lot better, because you're forced to separate these things out into logical units that should be testable. And going back to what I talked about much earlier, it makes it easier to identify when you have like a breaking release that might cause like a giant refactoring of code downstream, because you're able to have these testers that are like, oh, I have like suddenly all of my solver types are failing the interface test. I probably changed the interface like assumptions here, and those need to be refactored. So it gives you sort of a rule to point to and be like, yes, this was a breaking change. I have to make like a breaking semver release, and all my like project compat needs to be updated once everything is compatible with that. This is much better than dealing with method errors in my experience. So a couple of quick interfaces to look at. The first one would be chain rules. So chain rules is sort of the rule system that underlies Zygote autodiff in Julia. It's essentially a set of rules for how you differentiate through through functions that make up your program. And so chain rules really is an interface package where you're defining an interface for functions. And the interface to be implemented are these R rule and F rule functions that say this is how you differentiate in forward and reverse mode through my function. And so like that's chain rules, but chain rules also has chain rules test utils, which is a really cool package that does kind of like both kinds of like testing to your interface at the same time. It verifies that like, yes, the interface you implemented is correct, it conforms to that. But it also does something else, which is it verifies correctness at the same time, which is a really neat thing we can do with like an autodiff system because it's a relatively constrained mathematical problem. So what chain rules test utils does is it does like a finite difference approximation of the derivative, and then it compares that against your rule. And if those are within some like relative tolerance of each other, it says, all right, you got the differentiation rule correct. And so chain rules test utils is a fantastic, I think, approach to follow for these sort of like property-based testing ideas. The other one I want to look at for something that isn't necessarily on the testing side, but more on like giving you a common language for thinking about problems and uniting packages would be geointerface.jl. So geointerface.jl implements sort of common representations for geospatial data, or like abstractions for geospatial data with these various like geometry traits. And then in order to satisfy the interface, all these different geodata backends need to be able to convert their representations of like a polygon into this generic representation of a polygon, which can then be translated to all these other packages that also support the geo interface. So geo interface gives you this like really common language and really common interface for dealing with all these different like heterogeneous sources of geospatial data as if they were all sort of the same. So you don't have to worry about necessarily which package it comes from. And it facilitates like easy translation between them. And then you can start to write your algorithms in the sort of like common language of geointerface.jl rather than needing to specialize based on what the different representations are, which is a really nice feature to have. I also think there is a geointerface package later this week. I'm not sure what time that is. So now we're coming into kind of like the end of the talk. I have a couple closing thoughts that I want to end with. Interface management in Julia is still kind of an awkward thing because there isn't really like a canonical way of applying an interface. Should I follow the type hierarchy? Should I follow traits? Should it just be something that's implemented? There are like, until there is like a canonical way of, or like a correct construct in the language for doing that, I think that you should really just pick the one that works for you. And that may or may not align with one of the existing interface packages. A really interesting idea in this space, I think, is Duck Dispatch, which is a prototype package from Micah Ruffsfold recently, where they treat interfaces as kind of an ad hoc thing where it's like you implement these methods, ergo you implement the interface. But they pull some tricks to make interfaces something that are actually dispatchable, which I think is a really cool approach. I'm not sure that I would recommend it for like production code, but if it can be tightened up, I think that would be excellent. And finally, there's interface specs from Keno, which is focused more on like semantic interface definitions and verifying those interfaces. And finally, a couple of things to check out if you're interested in learning and thinking more about this problem would be Julia Lang issues 5 and 6975. Issue 5 is about multiple inheritance, 6975 is about interfaces. Valentin has a really good write-up in required interfaces on the concept of interfaces. Jacob Nissen, who's a very like active member of the Julia community, has a blog post called What's Bad About Julia. And in there he has a section where he talks about interface definitions in Julia, and I think it's a superb like summary of the problem. And I really would recommend looking at Keno's write-up in interface specs. I think it's very thought-provoking about what could become if we want to try to formalize this construct in Julia. So that's all I got. Thank you. If there are quick questions, I could take a quick question. I know we're short on time.
So thank you very much. I think you and I think we're not alone here that we think this is a weakness in Julia, maybe even that these abstract definitions, there's no canonical way to do this. But what is your objection to the Pythonic way of doing it, where you can't instantiate a concrete type unless it satisfies the abstract interface?
I think that if you are not, the issue that I take with the Python solution is that you need to apply the interface at definition time. And I don't think that necessarily follows with how Julia code works. Like, we want to be able to define structs that might not, like, at what point in the, like, defining of the struct do you also assign the interface? And at what point does it become something that, like, it can't be instantiated because it doesn't assign the interface? Or
So
does it?
at instantiation time, I'd say.
So maybe I don't need to fully. That might work. I think that adds a lot of overhead to then verify the interface unless we have a way of checking that efficiently. I suppose I hadn't. The main objection I took to Python was that you had to declare the interfaces at definition time.
Mm-hmm.
I think if there were a way to prevent instantiation of a type, that might work, but it might still be overly restrictive depending on what we wanted to do with the type.
Okay.
I haven't thought about that perspective yet.
Okay, perhaps for 10 minutes. Okay, 5, okay. But let me know if it's 10. Okay, okay. Okay, hello everyone. Thank you for coming. Today I'm going to tell you about the new package, AppBundler, which allows to bundle your Julia GUI applications. And the issue we're going to solve is that as Julia users, we are accustomed that we just send to other Julia user a directory, and it contains a manifest file, and we can simply say them, instantiate and run the include main, and you're done. And that if the world would work like that, I wouldn't have to give this talk today. But the world is more difficult as people expect easier ways to install applications, especially GUI applications, and they are not familiar with Julia. So another very common way is then, okay, we don't send the Julia to the user, we just put it in a backend, and then we put it, make a web app for that application. But there are some, and that's easy, but there are some advantages to deploying as local applications. So the first one is the performance. We can get a CPU and optimal code. We get access to GPU resources. We can access cluster and other things. Hardware interfacing. We can have some measurement apparatus talking to Julia. It's much nicer if we are on the same system. Offline functionality, obviously, security and privacy. Interesting for my interests, it's that the secrets and sensitive data don't leave the device. Another aspect why would you want to use Julia is because it offers better ergonomics, in my opinion, especially when coupled with QML. So, okay, so there are good advantages, but there are very quite a challenges which are not immediately obvious. So the first one is development complexity. So would the application run the same way on Linux, Mac OS, on Windows? Also, we need to maintain a separate package formats for different operating systems and also build infrastructure. There is a problem with distribution, so obtaining and maintaining signing certificates, navigating different marketplaces and submission review processes. There is also user adoption barrier. So users wouldn't be so willing to try your application, our web application, because you need to have some established trust that the application wouldn't leave the system in some corrupt state when your application is removed. There is also maintenance issue, so addressing operating system specific bugs and version fragmentation among the users. So all these are quite hard challenges, but let's focus on development complexity. So we also already have solutions for this development complexity, in the sense that Julia has artifact system and binary builder, which allows us to retrieve all the dependencies and all our GUI applications usually often work the same way on different systems. So that's a solved problem. Another solved problem is coming from the operating systems themselves. They have come up with the idea, is a good idea, that the applications need to be sandboxed, so they don't access more resources than they need, and they wouldn't leave the system in corrupt state because of some accident. So, and this is where AppBundler comes into the picture. AppBundler vendors package dependencies and artifacts, and offers post-processing scripts, so these applications bundles can be formed. And lastly, the deployment complexity can be significantly lowered if we use some continuous integration tool like GitHub Actions to create and finalize created bundles. Alternatively, the bundles can be sent over SSH as they are self-contained and finalized on the respective systems. The later is how it's actually used and debug these bundles. So the next step is to talk about the compilations. So we know that especially GUI frameworks are notorious of the time to first X time to when something shows up. So, and historically the solution was to use sysimages for that. So with that we had a package compiler, and it was related to the previous attempts to bundle applications with application builder. But since Julia 1.9, the package images became cached, and with Julia 1.11, now they are relocatable, and this is why it's interesting for also as alternative to sysimages. And also package images are more tested, and this was and the compilation process is more transparent, and we see the loading, how it compiles, and this is actually the main point why actually I chose package images, because the QML at the time didn't work with the package compiler, and as I not proficient at C++ and not willing to learn it, I chose package images as a solution for the problem. So, neither, it's important to mention, neither method offers cross-compilation support, and that must be combined with compilation must be combined with finalizing the bundles on the hosts on the corresponding systems where they are built. And this is not much of issue because the signing of the bundles happens. Usually the tools are not available to the one system, like signing the bundles. They are only available on the one of the systems. But things are improving with Mac OS, I have seen that the Rust people have managed to make quite a good tooling for being able to bundle applications on Linux for Mac OS on Linux. So, but there is no I haven't seen this much on the Windows bundles itself. So now it's a demo part of the talk, and let's make some bundles. Okay. So let's see how I can increase the font, increase the size. Let's see. So what we are going to do is I have created a demo repository and added to the schedule, and what it contains is 3 post-processing scripts and 2 applications we are going to discuss here. So the GTK application is there is nothing much in there. It contains a manifest file and project file and main.jgl, and in the meta we have a build file. Let's check that the application works as expected. So how we do it? We just start it in the corresponding project folder. Project folder, yeah. And so what we do next, if we would transfer this folder to other system, we would instantiate it, but it's already instantiated. So, and then we can run the main.gl, and we get that the GTK application works. So, and this is all that's needed. So we can now bundle it. So there in the meta folder, I have a build script for it. So let's start it in a project meta. And in the meta, let's start the build.gl script. And let's open this build.gl script and discuss what it do. So what we have is that from the app bundler package, we have a single function which we are going to use, a bundle app. And the bundle app, the first parameter is a platform parameter, which contains architecture, and also optionally you can put the Julia version. If Julia version is not specified, it takes the Julia version, checks Julia version from the build environment which you are executing the build. So you get exactly the same thing as you just run the main GL. And the next argument is where are the application directory. So we extract it from directory of the file, of the build file, and lastly, what is its destination. And okay, so we have finished the build, and we can proceed with finalization steps. So let's go to the corresponding finalization, where the finalization files happen, and execute make dmg GTK app. Let's see. So we get so after the build, we get four build objects, and we want to build it for macOS. So GTK so ARM64 application, and okay, so it works. And since it's going to precompile, it takes a little bit while. We are going to install the snap bundle which we created as well. So we have these 3 files, and we can install the snap bundle. So we snap install dangerous GTK ARM64 snap. Okay. And we put in a password. Okay, so the installation happens. So the first thing I need to mention that the dangerous flag is used because this bundle is not signed. And to sign the bundle, one uses Snapchat sign bundle, but I haven't actually tested that out. And what it does is, so you create an Ubuntu One account, and in the with a how you send your you create the cache of the bundle locally, and send it to the canonical. They sign it, return the signature, and it's a bundle inside. So it's kind of you don't own the key for which you sign the bundles. It's kind of interesting thing to learn. And now it's what it does is, so there was an opportunity with the snap bundles to do the precompilation at the configured script time. So the snap bundles have certain post-processing steps, and why not to do the precompilation at the post-processing step, as it enables, for instance, I'm here on I made it on Mac OS, so I can now distribute this bundle, for instance, on my Raspberry Pi. It creates some precompilation workload, and so it's much easier for me as developer to do so. Also, there is possibility to precompile it, and it's also supported with added in the documentation. So it's installed, and let's see how it works. Okay, so we have an icon, and we have it. So yeah, the application is very simple, and now it's so we have it finished with Linux. Now let's go back to the macOS. So the macOS have finished. We go to the build directory, and we have created GMG file, and voila, we have installer for our GTK application, which takes 1 gigabyte, but it's compressed in 267 megabytes, so it's reasonable. And so it's not there. Okay, it's here, and let's test it out. The first time it tries to verify the signatures and all the things, so it takes a little time. When we try it again, we will get it instantaneously. So, and I want to show also a more complex application which is built in a QML. And this is a Peacefounder client application for a voting system I developed, and I will be showing a demo tomorrow at the industrial talk section. So it is fairly complex. It has a storage of the directory. It uses actually quite nice QML feature, RQML nice features. It has shadows, and yeah, thanks to the QML package, it's possible to make it to make actually quite nice applications in Julia. So, and we saw that it opens only in 3 seconds, and so it's fairly reasonable and can be reduced if it's more optimized in that way. And finally, we need to discuss the Windows systems. So, unfortunately for Windows, there is a bug in GTK which prevents it from being run in the kind of sandboxed environment in which Windows offers for packages. So instead, we're going to install the Peacefounder client. And what happens? So you see, we press install button, and it installs actually quite quickly. And we see that it uses all system resources. So this is something which will going to be its future watch, which needs to be improved with the sandboxing. And it's installed. and I think it should be launching by itself. Let's see. 1, 2. I had a splash screen idea initially, which would you program making a OpenGL, but why doesn't it have? So okay. So first time it takes a little bit time because it also tries to verify the signatures of the application. But afterwards, I have measured that it takes around 8 seconds, and this is in a virtualized environment. So it's also kind of reasonable. And if you implement some splash screen, it's even more can be even more appropriate for different contexts. So we have made these bundles, and let's discuss what actually happened with the post-processing scripts. So make DMG script, which I used, is first execute precompiles, and the precompile file is in the bundle itself. So also the launcher is formed, and the launcher is needed because macOS wants to put the signatures inside the executable, and the bash script cannot be executable, is not executable. So how it's worked around that, I make executable that points to the bash script, and everything is fine. So it's code signing, and the code signing includes entitlements. Entitlements specify how the application is going to be sandboxed. So this is also put into the bundle for convenience, and also the neat installer made with a DMG build. So that's how the make DMG works. The snaps. So the snaps, as we discussed, needs to be installed generally with a classic flag, because the application also for GTK application there is possibility to make a recipe for I managed to make to run in a sandboxed environment. But general for QML application, they need to use a classic flag as it use in that environment. So configure hook, and alternative to waiting to post how during the precompilation during installation it's possible to precompile it, and also it's possible to sign. So when it's signed, then one can install with graphical installer. And lastly, with with Windows, we have a precompile script, and we need to change the subsystem for the LLD executable and Julia executable, because otherwise, when you open the Julia application, you get a terminal window open. But when you change the subsystem, you no longer cannot execute the application in the terminal. So it's quite a pain in that sense. Then the archive needs to be formed with make appx back command, and then the sign tool sign. All these three tools one needs to find, install on their Windows system separately, and it's a bit of pain comparing to what you are used to in Linux or macOS. So, but when you have it, you make an aliases for them, and they work decently. Some tips which you can use to make your applications better is you can use precompile tools to precompile the startup of the application on the workload. This is how actually what I actually use is in the QML application I showed you. You might need to use relocatable folders. I stumbled on the issue that I didn't have the QML files after I relocated them. When you debug the bundles on the Windows, you don't need to make them final bundles. You can make the directory structure and use the add appx package register command. And so this is, and while using it, you can change the source files of the directory, and they will be reflected on the bundle. And similarly, on on Ubuntu, you use a snap try application and snap run shell, where you get into the exact kind of environment how the application sees it. So the final thing we need to talk about is customization. So the customization is enabled with the recipe system. Every recipe is made of a list of rules executed sequentially. And the rule specifies files that need to be moved from the origin to the destination. And if the destination already contains the files, by the previous rule, it's skipped. And this is useful when I have a flat directory structure, which are the rule, and the bundles are very hierarchical directory structure, and you can make put files in hierarchical directory structure, and that will take precedence on the flat directory structure files. And also, this is a customization option that if a rule origin exists in app folder, it is taken from the default folder from the app bundle recipes. So what I can show you is a little bit what it looks like. So let's get into the Emacs, GTK. So app bundler. Need to make some both. So yeah. This way. So I have a meta folder in the psounder client, and you see there's quite many overrides. And similarly, I have in app bundler the recipes folder, and you see that the recipes, since the icon and the icons are in my meta folder, they take precedence of the recipe folder icons. And similarly, I have configuration for different files in I override the snap YAML file, override init file, startup file. I also override the precompilation startup file. So this offers quite many options to do the customization. And finally, sandboxing. What's about so the sandboxing? So the first thing is that your user data is stored in the user data environment variable, and on Mac OS it's there, Linux there, Windows there, and additionally there is user data cache directory is put as a first entry as a depot path in case some additional files are generated, and so they don't spoil the system. And so one thing which will be Linux and Windows, these are contain sandboxed directories. On Mac OS they are not sandboxed because I haven't managed to get to use this directory. You need to have entitlement sandboxing enabled in entitlements, and there is a issue with starting Julia applications in that environment. So applications marketplace often expects the applications to use the last number of system resources to get for favorable reviews. So, but currently none of the recipes works. So macOS application loads, but is unresponsive to input. OpenGL does not work with QML and GTK, but works with GLFW in the snap containers. It's snap bundles. So I don't know what's happening there. And the Julia doesn't load in Windows in the sandboxed mode, but there is good progress made in the issue, where the idea is that you need to load every DLL separate before you start Julia process separately. And yeah, there are some interesting things which can be done on the hackathon project. You can get in touch if you want. We can write a GitHub action that automatically bundles applications when the new version is tagged. So would really make my work a lot easier. Some people might prefer Flatpak, so Flatpak recipes can be made with the same system, which not very complex I have made. And yeah, adding a package compiler super, but I don't know what's going to happen with the Julia compiler. So in the whether this is going to be relevant. So and this is the end. So perhaps questions and.
The binary that was created, did it bundle Julia artifacts and the packet source? Did it bundle everything?
Bundles everything. Everything, yes.
But nothing is precompiled. The precompilation happens after.
Precompilation happens on the host system with the post-processing scripts. Okay, I cannot. Okay.
The question was like, did the bundle, the bundle that was included, did it contain Julia?
Yes.
Source and source files and the artifacts as well.
Yeah. Yes. Everything.
No, we have to wait. We should wait 10 minutes. That's what I'm saying. Yeah, because people might log in online to see the stuff. So we should keep to the schedule. Yeah. So yeah, this guy doesn't seem to be around, so we'll wait 10 minutes and start then. Unfortunately, sorry about that.
This mic is not working, right?
Yeah, it's also working. It's better to use this one. Okay. Created stars that extemporize? No. So tell people what the project was all about. Coastal. No. Yeah. For people who just came in, the dictionary stops, the author isn't here yet. So we will start the next talk on the schedule in 7 minutes time, which will be that one, but we are waiting for the schedule to allow us. If you really need to know about hashing for dictionaries, talk to Chris.
I'm frowning. Dr. Jameson. Jameson was the other mentor on the wall of the
Dr. Jameson, yeah. Sorry about that, but
Welcome everybody to this track session. We will start with Surya Kiran Peravali, and we have his presentation with title Simulating Nanoparticle Trajectories Using CMinject.jl. Surya, you can start. You have 10 minutes.
Hello everyone, I am Surya Kiran Perwali. I am a researcher at Deutsche Electron Synchrotron DAISY, which is a particle accelerator laboratory. Today I am going to talk about a particle trajectory calculation tool called CMinject, which assists our experiments at DAISY. DAISY is equipped with several kind of particle accelerators, like you can see here. The one which I'm going to focus in today's presentation is called European XFEL. XFEL means X-ray free electron laser. This is like a 3.4 kilometer linear accelerator, starting from our campus DAISY to 3.4 kilometers. Here electrons are accelerated at the speed of light in order to energize them, and eventually this electron energy from this electron is converted in form of X-ray photons. These photons have in the range of femtoseconds. These pulses are in range of femtoseconds, which enable us to record molecular motions and also study ultra-fast chemical reaction, which has significance in healthcare industry, medicine research, and also material physics. So eventually, this X-ray pulses are directed in to our experimental halls here, which is almost size of a football stadium. So you can imagine the scale of the experiment here. So whenever this particle, when this X-ray beam hits a nanoparticle or a biomolecular protein, what happens is it creates a diffraction pattern which can be recorded. So by collecting several of these diffraction patterns, we can process them and we can construct a three-dimensional structure of this biomolecule or a nanoparticle. So the major challenge with this experiment is called single particle diffracting imaging, by the way. The major challenge with this technique is how can we accurately, efficiently align this particle to the X-ray pulse. So we use typical aerosol injector, which operates at different background gas pressures, right from atmospheric pressure to ultra-high vacuum. And also, we use a technique called aerodynamic lensing, which collimates the particle beam. Like you can see the colored lines, the particle beam gets narrower and narrower until near the so that at the X-ray focus, the particle is having the maximum density at the point. So optimizing this aerosol injection system is we need a numerical simulation tool in order to run a design optimization. So we created CMinject, which follows two steps. First, we have to have a simulated flow field data converged to a steady state solution. This is another complex multi-physics problem, which I have to use a Navier-Stokes hybrid Navier-Stokes and Boltzmann equation solver, which I created and benchmarked with a rocket nozzle case, which is which also follows a similar physics. So first, once the flow field is estimated through this hybrid solver, the next step is we calculate particle trajectories. So basically, CMinject.jl, what it does is it reads the it interpolates the force fields from the fluid flow to the particles, and we solve a Langevin equation, combining drag and Brownian noise. So this is basically a stochastic differential equation. So this stochastic differential equation is very simple to implement in Julia. First, we define a stochastic differential problem using functions of drag and Brownian noise, and then I ensemble this problem in order to run parallelly, and then solve this problem using a suitable SDE solver and also an algorithm for multi-threading, that is ensemble threads, which I used here. So this tool can calculate in 2 dimension and 3 dimensions. Now let's see how this tool works how this tool performs in comparison with the experiment. So here is an experiment of focusing 25 nanometer gold particles. You can see the semicircular part is the place of the vacuum chamber where the X-ray is focused. So you can clearly see the particles are getting focused and defocused. So these particle beams can be widths can be measured at different distances in the vacuum chamber. So these dots in the left side represents the measured beam distance at different distances, and the line you can see is the simulated simulated curve, you can clearly say that like it follows the experimental curve, and also it can accurately predict the focus position where we have to align this X-ray also using the simulation. So we initially created this CM inject framework in Python as well. In Python, the implementation is a bit different from Julia. However, both the Julia and Python frameworks gives the same result. Now I would like to compare Python framework with Julia framework. So this is the comparison of performance between in 2-dimension, 3-dimension simulation between Python framework and Julia framework. What you can see is like at higher particle numbers and also at higher dimensions, the Python framework is showing a better performance, have a less runtime than the Julia version. This is due to because we optimized Python framework quite well with packages like Numba. We Pythonized some calculation functions and also multi-processing things as well. Where Julia, it's still a prototype version where I used only one utility, the ensemble threads, which I mentioned like one slide ago. So, and also another thing, what I did is I did profiling with my Julia code. You can see the flame graphs of simulation run on 4 threads and 16 threads respectively. And this is on the simulation on the main. These are the call functions on the main thread. You can see from 4 threads to 16 threads, the scaling is improved for most of the functions. But however, when the initialization of sol.jl in differential equation package, so this is not properly scaled. This is due to some garbage collection issue with this ensemble threads particularly. So either I had to use a different algorithm for parallelization, or I had to implement this. I need to tweak the code in certain way that the performance is enhanced, which is current work under progress. On concluding notes, I would say like we created this CM inject tool in both Python and Julia frameworks, and both the Julia and Python frameworks give the same results. Our Python framework showed a better computational efficiency compared to Julia, particularly at higher particle numbers and higher dimensions. However, we invested a sufficient amount of work on Python framework to achieve this one. However, there is still a scope on Julia framework, which can be improved in coming weeks. However, Julia, according to my opinion, I would say like Julia is more user-friendly and syntax-friendly. For example, I have a background in aerospace engineering with expertise in fluid mechanics, basically, and I'm not like a high-performance engineer or something. So usually doing performance engineering is quite a hard task for me whenever I create my codes. So I always prefer user-friendly codes in which Julia has a better advantage. And moreover, this code has to be used used by experimentalists for their experimentation. So in order for them to understand the codes, it's easy to have it in symbolic form which Julia has. So there, the Julia has an advantage. So this project is in a collaboration with our DAISY and University of Federal Armed Forces in Germany. So I would like to acknowledge my colleague Simon Welker, who was the core creator for this CM Inject Python, and also Johan, who introduced me to Julia, basically. Thank you very much for the opportunity.
So we do have some extra time also for questions, if you have any.
Yes.
Do particles interact with each other? Like, could they be charged?
In some cases, yes. If there is some kind of electric charge between them, they do interact. But in this case, particularly gold nanoparticles, something, there's not like they are not ionized particles or something. So they typically don't interact in this one.
Okay.
Thank you. Any other question?
Do you run this on an HPC cluster, or can you run this locally?
I run on a HPC, but it's only a single compute node. So.
Any other question? Seems not. So we do have here the next speaker, Johan Hidding.
Johan, yeah.
Johan Hidding, okay. He his speak is going to be about natural science, computer modeling, and literate programming. So you do have 10 minutes from when the microphone is placed.
Is this working? Yeah? Oh, yeah. Okay, let me... There we are. Okay. Thank you. My talk is about Entangled. I'm working at the Netherlands eScience Center that's located in Amsterdam. At the eScience Center, we work with scientists all over the Netherlands from all disciplines. And our main focus is to improve the usability, reusability, reproducibility, and all the quality aspects of the software that is being used in scientific domains. So, yeah, it's a bit of a broad scope title, but the idea is that I will present you with kind of a workflow of how we can do science. Let me switch tabs here. So this is quite recent. This is work that I did like I think 2 weeks ago. I started this. We have a model, and this is about sedimentation in seas, and we needed to implement some transport model in this. So there's a you have some documentation. This is a Pluto notebook. Anyone not familiar with Pluto here? Okay, awesome. I love Pluto. So it's really great, and it allows you to put documentation in between your code, and in this way establish a human readable narrative next to where you start to implement this code. And what I think is important to understand here is that we're not just programming for the computer to do things, but we're programming also for our colleagues to understand what we're doing. And in this case, this is a very direct communication between me and the lead investigator of this project. So say, this is my shot at the transport model for our model, and what do you think about this? So there's some testing in here, and then here at the end you see that okay, some matter is being transported, and it's being produced at the same time. So it's wonderful. But now we want to go to the next stage. I want to put this kind of a proof of concept of this model and put it into the larger code base of the model, which is a Julia package, but I want to retain all the nice properties that I have from the literate programming. So I will immediately present you with the result and show like, okay, we can do this. This is documenter.jl. Everyone is here familiar with documenter? Cool. So this is all typed in Markdown. I add some nice figures to illustrate the concepts, and then we basically get the same code again. This time, all my code is in Markdown code blocks, and I give them names. So you see here that I added a little tag saying, okay, this code block is example active layer, and here we have a file, source transport active layer. This is actually a module, and I can continue with the previous code block. So I don't need to put everything in order. All of the code can be wherever you want it to be to give you an optimal narrative from a human perspective. And this is the original idea of literate programming as it was first invented in the 1980s by Donald Knuth, who is the grandfather of a lot of domains in computer science and also with literate programming. You see the same plots here, but now these plots are actually being generated using code that is now somewhere statically inside a Markdown document. And I add here some commands that is being parsed by a component that turns this into a workflow. So not only is this being plotted, but it's being stored. So I don't need to recompute things twice. It's just done once until the code changes. So for example, there's requires, which means if this file changes, then also update the plot. Okay, so now the question is, how does this work? I gave you a little bit of a science story. We moved from a Pluto notebook or a Jupyter notebook to code that's just based into Markdown. How does this work? And the magic behind this is what is entangled. So entangled, no one can be told what entangled actually is. I will show you. If this works. Just this morning this worked. Okay, I will. I am not online, am I? Yeah, apologies for this. Internet. Can I have internet? Oh, there's my internet. Sorry, I just put up a hotspot. There we are. Yeah. So this is an editor where you have, in this case, Vim. It can be any editor. And here you see I have the entangled daemon running. This example is in Python. Entangled works in any programming language. So if you have a Fortran project lying around and you want to do literate programming in Fortran, you can do it. In this case, it's Python. So you see that automatically this file is being created because we put it here in the Markdown metadata. And you can decompose the program into different code blocks. You give them names like this. You say hash factorial. Now this code block is named factorial. And then refer them to them in other code blocks, and the order doesn't matter. So now using these, this is no web notation. This is also, I didn't invent that. It's from the 90s, I think. Okay, now there's an error. What do? We don't want to debug from a Markdown file. That's just terrible. So we open up the Python file that was generated and start to edit in there. And now you see that I fixed all the errors. And you see that those changes were actually propagated back to the Markdown. So, thank you. So this means that we can still have all the facilities that we're used to from the IDE, the syntax highlighting, everything just works. You can develop like you're used to, fix bugs like you're used to, but you don't have to do it in Markdown. So this, unfortunately, this is a Python module. I would love to have this as a nice binary package. I don't know, but so you'll have to stick with pip for this one. But you can use it with any language that you like. And last slide. So entangle.github.io, very easy to remember. There's some information there. You can rewatch this animation if you like. If you want to contact me, this is my email.
Okay, thank you very much. Very nice presentation. I would take also the chance to clap the hands for the presentation of Surya that we forgot before. Okay, so questions for Johan.
Yeah.
Any question?
Yeah.
Okay, we have one there.
Hello.
Hi.
So you made the Documenter website with Entangled, right?
Yes.
Cool.
Well, so I actually had to hack a little bit into Documenter. So if you're interested, I can show you. I had to transpile the Markdown to a second version to a second Markdown version, and then compile it by Documenter.
How does this compare to Emacs org mode?
Org mode is terrific. I've tried it for half a year or so. It's really nice, but it only works in Emacs. I mean, I know that there's a VS Code mode for org mode, but it's not quite there yet. So if you do this in org mode, you force all your collaborators to use Emacs. Also, org mode doesn't have this reverse capability where you start to hack into the files that are generated and then translates them back.
Any other questions? Okay, let's thanks again, Johan. We do have now the next presentation of Team Zlen de Broek.
Pretty good.
So it's a 30 minutes presentation. We will show you the yellow card. That means you will have other 5 minutes.
Yep, we're live?
Yes.
Okay, great. Hello, everyone. I'm Tim Sanderbroek. I'm from San Diego. I work for General Atomics. I'm a physicist and software developer. And I'm here to present to you Fuse.jl, the power of Julia for the Fusion community. This has been a huge collaborative project with many, many co-authors. So, you know, it's not just me, myself. So what actually is Fusion? Let's go with that. So Fusion is kind of an energy source. It's very naturally occurring in all throughout the universe. You might know them as stars. They're kind of like big plasma balls, and they're gravitationally confined, and then they kind of generate conditions such that fusion can sustain, and that's kind of like opposing the gravitational force inward. You get a nice balance. These things are pretty large, and they have tremendous amount of energy output. So we want to use the similar concept. We want to also use fusion on Earth to produce electricity. So how do we do that? We cannot use the same methods because we just don't have enough stuff here to kind of like confine gravitationally. So we have to use a stronger force, and that's kind of called the magnetic force. The biggest and best contender right now for this concept to work is the tokamak, which is much smaller size, is an order of 10 meters, and we're trying to aim for a net output of like a gigawatt of power. Here you see a cartoon picture of the kind of magnetic structures inside of a tokamak. And in particular, you can see here, let's start with that, those field coils here, they're called the toroidal field coils. Then if you run a current through here, you generate a magnetic field in this direction. That's kind of called the toroidal field. And then you ramp a current through the central solenoid here in the middle. And then through transformer action, you kind of introduce a plasma current in the same direction, which if you know from high school, if you do the right-hand rule, you generate a poloidal field. If you combine those two fields, you get a nice, like a helical kind of shaped field. That's kind of like the black one here that kind of goes around, and it's like winded. And kind of a key thing to take away from this is that you want them to be very winded, because that's kind of, it turns out to be the safest way to operate this. Because if you run at like a low safety factor, this is Q here, the plasma will start kinking itself and throwing itself into the wall, and you get a major disruption. So let's focus in a bit on the plasma here. So from the hot fusion core to the cold edge. So here you kind of see the same picture, but now like focusing on the plasma. And you can see that it's kind of a self-organizing magnetic topology of the plasma, where you see this kind of like a cross-section, where in the deep core you have a very hot plasma, and then like when you go outward, it gets cooler and cooler. Because at the edge, it needs to be connected to the wall. Like as you can see, this is a picture of the tokamak, where if you follow the kind of the loss closed flux surface here, you will see it hits the inverter. So it has to be cold on the edge, and it needs to be very hot to kind of generate the fusion power. This is a toroidally symmetric structure, and you can kind of like represent all your quantities in 1D. It's kind of like the row you'll see like further in the presentation. This row kind of is the coordinate. Interestingly, if you look at this figure here on the right, you see that fusion power generated in the sun on average is much, much lower in, like if you take a cubic meter, there's a lot less fusion power being generated that we're trying to aim here in the tokamak. And the way that we can kind of achieve that is by going for the most like reactive like fusion cross-section reaction, which is with very light isotopes, namely with deuterium and tritium. Deuterium is like naturally abundant everywhere. Tritium, however, we have to kind of like self-create, and we do that by using the neutrons that we create inside the deep core, like right in here, and that's then gonna like hit the blanket, this kind of like orangey-looking structure here. There it will react with lithium and then produce your own lithium. There's some other features here. There's kind of like very close to the super, super hot core. You have things that need to be extremely cool, like the superconductors, like the toroidal field coils. So you need things like heat shields in order to make this happen. So where are we today? There's been many, many tokamaks built and operating all around the world throughout all continents, but none of them are producing net electricity. So we're here to, let's deliver fusion energy to the grid. And let's now kind of like say where fuse fits in. So there's a bit of a problem with the traditional concept and design workflows, where there's like their broad system code analysis to target like individual designs. Expert then run high fidelity analysis on each subsystem. But unfortunately, when you do that, you run into major issues because you have a wide array of like domain experts that can't quite agree and will start to diverge on the concepts. This will also kind of lead to premature design lock-in that kind of limits your exploration in this huge like optimization like space. And many of this then kind of becomes manual integration and kind of disparate analysis instead of like a cohesive, like holistic view of it. And that's what we're trying to bring. So that's kind of like our goal, to bring a holistic framework. So the needs for this framework is to go from an idea to concept design in minutes rather than months or even years, evaluate wildly different concepts just along the same footing, provide different physics and engineering teams a high quality integrated representation of the design, and then you can support the modeling needs all the way from design to when it's running, because there's also like control. And the more you know about your physical system, the easier it is to control. So a quick outline of this talk. I'll quickly go over what we're doing in the framework, and then I'll explain some plasma physics models, engineering, plant, and costing. And then kind of my exciting part is like showing you how we do kind of machine design and kind of large multi-objective optimization, and a little bit of wrap up. So starting with the framework, it's developed from the ground up based on our modeling experience and other frameworks that we've built in the past. It really revolves around build data structure that's kind of like became an international standard, the ITER IMS standard. And this kind of enables like a huge fidelity hierarchy of different models that you can run on the same data structure. And all of this is developed in Julia. So while we support the whole fidelity spectrum, what I mean with that, like there's like first principle codes all the way to like little analytical expressions for specific physical phenomena. So all of it is that is supported, but generally try to balance fidelity with speed. And then we try to use machine learning to get like to almost real-time speed at high fidelity. So we strive for sufficient fidelity to get the interfaces between subsystems about right. So expert in-depth studies should not have to find huge mistakes in the designs. And after that, be as fast as possible. So modeling a fusion power plant is quite complex, as you can kind of see here, because there's not only the tokamak to consider, there's like all these different subsystems. There's things like neutronics, like blankets, like balance of plant and costing. So traditionally, it's done by a huge team of experts, taking months up to a year. But we made something that can kind of run automated and do all of these different analyses in together. Kind of that brings to a speed up, if you can run in about a minute, of 500,000 times than what we had before. And that also means that you're just limited by compute and not by man hours. And it will save you a lot of money, of course, if you do it that way. Going over the plasma physics models. So plasma physics models is kind of like bringing all the different physics models together, because there's many, many different like ways that you can look at the same at the same plasma. And one of them is kind of like the equilibrium of how it's kind of like defining the geometry. So here you see, for example, some simulation results of how you find those kind of like magnetic field line topology. Then we go like towards like some transport and heating and current drive. That's kind of like briefly said, the plasma does not want to stay very hot. It wants to spew all its like energy and particles out, and that's kind of known as like turbulent transport, while you're trying to heat it at the same time and also have self-heating from fusion, of course. This method is like tightly coupling the transport and the heating together, such that you find a balance between the flux outward and inward, as you can see on the figures on the right, where you have like the total sources in blue, and then like where you have the total transport, which comes from different channels, adding up together. Next is you have a current density that, like I was talking about, the plasma current that's going around. That is, of course, also a profile in the same like dimension, this row space. And this needs to be updated to get to your next iteration, because the way that this works is that all of these different pictures are coupled together, because they all are depending on each other. For example, you cannot really do transport without the geometry, and you cannot do the equilibrium without having like some current density profiles. So you run this many times, and then at some point you kind of reach self-consistency and convergence. So does any of this work? It sounds nice that you can do this very fast, but does any of this work? So let's compare fused plasma models with experiments. So here on the right, you see kind of like a plasma shot, the temperature profiles of a plasma shot being locally run at General Atomics in San Diego. And you see the experimental results, like with error bars in blue, and then the matching results from fused in orange, showing a pretty good agreement for this kind of complicated system. So that's just one single tokamak. We've also done large multi-machine database studies. We have the tokamaks that I've kind of described earlier from all over the world, from the small ones like Compass and TCV, all the way to the ones, the ones in the UK like JET. And you see a very good agreement between the predicted energy confinement time, which is kind of like a global like metric of how well your confinement was, against the experimentally recorded ones. So this gives us kind of good, confidence that our models are working as intended. So next up is very important other stuff, is kind of like the engineering and the engineering aspect. Because plasma physics is fun, but it's not the primary component actually. So we're able to do automated tokamak builds, where we go kind of from 1D radial, where we kind of base requirements on like very technical like stress limits and things like maintenance and neutronics, to 2D cross-section, where you're introducing things like diverters that have to take up the heat load. And then we can all the way go to 3D CAD via GMesh. So, and then you can use mesh generation. And then, as an engineer, you can take this and do any of your heart's desire, if you finite element analysis on these kind of like end result designs. So another thing to talk about is kind of the superconductors. Superconductors have a certain critical current density that they can run it. So how much current you can pump through a loop, to a wire. And they're kind of limited by an external magnetic field. So you kind of, there's different types of superconductors. There is the low temperature superconductors that we have already built, like the ITER ones. And then there's the high temperature superconductors that the field is actively working towards. So here you can kind of see that the ones that we currently have, the green ones, they're kind of sitting at the low end of the spectrum, and that these new blue and like orange one kind of like expand this phase. Another kind of thing that you have to consider is I talked a little bit about the TF coil, like a magnetic field, and the ohmic solenoid, the central solenoid one. But you also have to kind of like shape the plasma. As you see here, the boundary needs to be along this surface here. And the way that you do that is by kind of optimizing the poloidal field coils. So these are like coils going all the way around like this, which you can set at certain currents, and then that will pushes or pull the plasma into this particular configuration. So you're trying to do an optimization along this rail such that you have your control points around here are matching to your plasma shape, as well as your target needs to be right at this diverter where it can take up the most heat load. And here's a showcase that even if you flip like kind of the plasma shape, the build and everything, and the poloidal field optimization works just as intended. So next up is neutronics. Neutronics is another important thing, because I briefly mentioned we need to make our own fuel. So there's a huge amount of like neutrons being generated right in the core, and then they're shooting in every which way. So you kind of have to do, you have to count up where they're hitting and how much tritium you're producing. Another thing is, we're creating 1 gigawatt of power inside of this like rather small area, and it needs to go somewhere. So this is kind of another challenge that we have in tokamaks, is that we have a lot of heat, the plasma touching the diverter. So here you see kind of like the flux hitting the diverter regions, and then you have like the neutrons being generated and hitting the first wall here, as well as kind of radiative emission from the plasma itself. So this is a way that you can kind of design your first wall such that you're below the amount of megawatts per square meter that your material can withstand. Last but not least, we're also looking at the kind of like sophisticated bands of plant models that provide kind of realistic thermal conversion cycles. So remember, I showed you just the 3 kind of like main points where the energy kind of comes out, and if you put those 3 kind of like this in the loop, you have kind of 2 main cycles that you can transform your energy from thermal to electrical power. That's either the regenerative Brayton cycle or the feed water Rankine cycle. The Julia has been quite great for this, because we can use modeling toolkit here, as it's a nice little like graph that you can connect, and it's validated against like thermal flow, which is kind of like a state-of-the-art like thermal engineering tool. Another thing that is we should consider if we want to make this commercially viable is the cost of all of these like components, because who wants to build a machine that's too expensive? Because nobody's going to pay like $10 for a kilowatt hour. So we're synthesized like 2 different like models in literature, and kind of updated them to like present day, inflation and like new technologies like high temperature superconductors. And this will be very useful for when we're doing machine design, which I'll go over right now. So Fuse is, because of the speed, it's kind of the first tool in which, for Fusion at least, where you can use kind of like multi-objective constraint optimization workflows to explore a very large design space. And the best kind of tool, like shout out to MetaHeuristics, is a genetic algorithm, where you find solutions that then steer towards your Pareto front. So for example, here you have a two-dimensional multi-objective optimization. On the one hand, you want to minimize capital costs, and on the other hand, you want to increase this was the safety factor from before. You want to make this as large as possible. So the genetic algorithm will then kind of push your front to and create a population of which they're Pareto optimal. Because the reactors here, right at this point, are the cheapest, but they're not as safe, while they're here are very safe, but very expensive. And then you have things like investors and policymakers who can kind of like figure out how much they would want to invest in terms of the safety factor. It's incredibly scalable, where we can use like HPC systems because it's super parallelizable. We can run like 100,000 cases in a few hours on a small cluster. And this is also kind of a formidable stress test of your tool, because you're running the entire design space, to do these kind of like, you find the most number of bugs in the craziest way possible. So here is kind of like a design study, or where I'm trying to compare kind of like two different like plasma shapes. This is kind of like all the rage in tokamak like physics right now, where you flipping the triangularity. So here you have a normal shape, or like this, and here you're flipping it, which has very different properties, but we're not quite sure whether or not it would actually be able to be viable in terms of, like, it has got a lot of good properties, but we're not sure if it would be viable for the confinement metrics. So this is kind of what the optimizer is doing. This is a 2D histogram. So where the x-axis is kind of like the generations in time. So initially it's fully randomized, like in this actuator space, and you'll see that it's unable to produce net electricity. One of the constraints that it needs to go towards is that it needs to produce at least 200 megawatts electricity. So after some generation, it finds how to do that, as well as the other constraints. Then you can see that the optimizer is, once it finds like a viable population, then it really pushes it down towards minimizing the capital cost. And lastly, you kind of have this 2D trade-off again, against capital costs against safety. And you can see that in color here, you can see that the cheaper ones are smaller and at lower field compared to the more expensive ones. So basically, this is kind of indicating that you can buy plasma safety with larger and higher magnetic fields. Here is the red one is kind of the negative triangularity one. So it sits far above the positive triangularity one, which means that it's more expensive, as we kind of expected, compared to the positive triangularity one. But there's other considerations, like, I won't go into detail because it's quite complicated, but that need to be considered in order to count them out. And so a kind of like a risk factor kind of idea would be another wonderful axis to put on this to kind of capture these other effects. So here I'm showing kind of a new technology versus a very robust one. I was talking about the different superconductors. So right now we have working low temperature superconductor, which are the dashed lines here. So you see that this space is rather small compared to getting to new technology. So this kind of tool is also kind of a way to see what kind of technology developments would bring what benefits. And then let's go over the wrap up. So we're open sourcing Fuse to the community, as it will be a powerful platform for integrated simulations. We already have imsgd.jl open, which is kind of like the data structure under the Apache 2.0 license. But the rest of Fuse will be open soon. And this is like 25 packages with at least 200,000 lines of code. And here you see a nice little word map of all the packages that we have. So what's been our experience with Julia? The pros and cons and kind of our perspective. So we really enjoyed writing code in Julia, as it's very high level like Python. It's fast to see, but you have to definitely put some effort in to kind of reduce your allocations and do profiling. But once you do that, it's very, very performative, just like Fortran, because most of our code base is in Fortran, so we're kind of like porting and rewriting everything. And that experience also has been very insightful. There's a lot of time saving. Like the last presentation kind of went over Documenter. Like you don't have to do that much extra in documentation compared to like older codes. Cluster integration is easy. You just like install you download your package, and then you're almost ready to go as from the get-go. We are using makefiles to manage our 25 packages, but when we're working towards like properly like releasing them, then we will use a registry and like use proper version control. There's been sizable improvement to Julia as we experienced over the years. And it's been actually pretty reasonably stable for, depending on at least 600 dependency in our code base. We've been trying to use auto-differentiation, but it's hard to keep everything like auto-differentiable. But that will be the goal. Some colleagues that are working on kind of like the like large HPC problems that run like months and months on clusters. They've also been trying to use Julia. They've had some difficulties, like coming from like Fortran and being really expert in MPI and all that stuff, to resolve the type instabilities that kind of come up. And it also looks like the Julia build system is not quite ideal for HPC users, as they're quite limited to, they don't have as much control over the cluster environment with specific hardware drivers and such things like that. So a little shout out to Julia Hub, to Steve Kelly and Michael Bolagna, who helped us with some speed ups to reduce some import time and code execution, compile as an executable, and working a little bit on memory management using distributed. To conclude, Fuse is a major leap forward in the whole facility modeling capabilities for the Fusion community, and we love to bring many of our people to Julia, and it will be great because right now we're using kind of a Python framework. It's a Python framework. There's always more to do in the near terms. We're applying like uncertainty qualification and risk, and we're always on the scout for better and reduced models. So this was my presentation, and thanks for listening. Are there any questions?
Thank you very much for this presentation. I think it was the most complete presentation I ever saw regarding fusion energy. And I did my PhD on a floor at the TUE where they were also doing fusion research. So that was very, very complete. Do we have any question? One there.
I was curious about the motivations for moving things from Fortran to Julia. Like, could you have left some things where they were, or was the big benefits you were gaining by porting them?
So the biggest thing is kind of having like a clean slate, like to really develop from scratch, and especially when because we're mostly coming with like plasma physics models, right? Like really highly computational like things. But when you're developing something new, it's very nice to use Julia. So it's mostly, like kind of like porting some packages, and then you have it all in one system, so you don't have the multi-language problem anymore. That's kind of like the design philosophy. So everything is tightly coupled instead of like a file-based system.
Thank you.
I do have a question also. So when you convert your code from, for instance, Fortran to Julia, do you think large language models can help you with that?
Oh, we're absolutely using them all the time. We had actually like a bachelor student who came and worked with us, and he was able to port like a huge Fortran code into Julia. And now we have our own Julia version of that, and he was able to, it was quite amazing.
Yes, I was just wondering about the physics models for the plasma, because I also did a PhD in plasma physics many years ago, and I remember they were very tricky. Plasma modeling was not easy. I guess the Fortran codes had developed quite a lot, but were you able to leverage some things in the Julia ecosystem to make it easier to re-implement these models? Or was it a case of really you had to redo the code from scratch?
So there, you learn a lot from the codes in the past, right? So you already have a really huge understanding of where you're trying to go. And on top of that, there's also been a lot of reduced models made by the community. For example, when we're talking about turbulence here, there are huge supercomputer models, but there's been kind of understanding of what's actually driving the transport, such that those are things much easier to implement.
Okay, thanks. Thank you. Any other question?
So you have multiple submodels. Do you validate them separately?
Yes, yes. So we take them also out of literature and like you say, you validate them on the tokamaks that are already running. But not everything you can, of course, validate because we don't have tokamaks that are producing net electricity, right?
So how? What do you do then? You need to validate it somehow because you based very important and expensive decisions based on the output.
That is correct. So part of it is you running it on an existing data set, right? Like that we have on all these tokamaks. And if you're using the same exact model for all of them, you have kind of like a confidence in extrapolating. The inverse of that would be using kind of like really hacky system codes that are kind of this linear regression on data sets. And so will always be a step up from using linear regression, which is kind of used in the tokamak community right now. So you can, of course, not validate your models on a thing that doesn't exist, but this is the best we can do.
Okay.
A question here.
You showed this cost estimation. How's this done?
So that's a good question. Costing is definitely a really tricky one. So there's things like material costs. You just need a certain amount of lithium, right? That has a unit cost, and you can kind of keep track of that in industrial costs. And then you have components like external heating, like gyrotrons, that are very used everywhere by the fusion community around. So you also have a good estimate for those. The tricky ones are the ones that are like the expensive superconductors, right? Those are not fully fabricated with large scale, so you kind of have to indeed make some estimates based on past and extrapolate outward and kind of estimate it. So although the absolute number of the costs might not be super correct, what is really important is that you get the relative cost when you're doing these design studies, because that will always be true. Like if you're using less material, it will be cheaper.
Okay,
thank you.
I think we don't have more questions. I just have a very fast question. When do you think we will have fusion energy?
That's always a good one. Yeah, it's a tricky answer. I don't know. I hope to see it in my lifetime.
So you think 10, 15, 20 years?
Yeah, I believe the tokamak will be the first to do it, and that's why let's not do predictions. I kind of also see it more as a multi-generational project in some sense. It carries much further than your lifetime.
Okay, thank you very much, and let's thank again Tim. We do have now the next presentation of Pere Mato. Okay, it's going to be about HENT 4.jl particle transport in Julia of physics and quantum chemistry. You do have 30 minutes.
Okay, thanks.
You have to go. Okay.
Okay, thank you. Yeah, okay, thanks. Thank you for this opportunity. First, I want to introduce myself. I am an applied physicist at CERN, the European Organization of Nuclear Research, which you may have known that our flagship project is the Large Hadron Collider. I have been for the last 17, 20 years leading several development projects on software to provide common software to the experiments, not only at CERN but elsewhere. And at the beginning, 20 years ago, I was one of the first to introduce Python to combine with C++ to make it easy for whatever configuration, analysis, and so on and so forth. So you may know that high energy physics experiments consume a large amount of computing resources, in particular on the simulation, which is the topic of this presentation, but also in reconstruction, and there is Graham's talk in 1 hour from now, and on data analysis. Speed is very important. Therefore, we use C++ in most of the places, but also the ease of use is also very important. And the community has developed ways to deal with these two language problems of C++ and Python, but certainly we pay a price. Now, we want to evaluate if Julia really can help us on this problem. And one way of doing that is one of the important things that we need to assess is the interoperability with existing C++ libraries. Okay, the community has been developing for many years, millions of lines of code. In total, perhaps there are 40 or 50 million lines of code, and certainly you cannot start from scratch. This is not feasible. So in this evaluation, one example that I have been working on is this JAM4. I'm going to introduce in a second. This is a simulation framework, which is extensive, is very complex, and is very challenging to rewrite, and is used by basically all the experiments and more. So the outcome of this evaluation will be to introduce these new functionalities in JAM4, and which perhaps this will be an add-on to the existing C++ code to make it more accessible to potential users which have perhaps somehow limited C++ experience. So JAM4 is a simulation toolkit for simulation of passage of elementary particles through matter. You take particles, electrons, gamma, whatever, and you do step by step the interaction of this particle with the atoms, with the nucleus that it finds. Okay, so it combines many models following the full range of energies on the different models that will interact these particles with the matter. Particles will produce secondaries, and then you track these secondaries, and so on and so forth. So it's a very lengthy process, and you collect all this information during this tracking. Now, this is primarily used on the fields of high energy physics, on nuclear physics, on the medical, on the space science, and many other things. Okay, whatever you need to understand what's going on with some radiation or some particles interacting with the material, you can use this toolkit. It's developed in a large international collaboration, the JAM4 collaboration, and is an open source license, over more than 2 million lines of code of C++, and has been developed for more than 25 years, so it's a rather complex piece of software. Now, the way I handle that is I want to wrap the C++, and I want to make it available to Julia. For that, I have been using this package, cxxwrap.gl, which basically it works like the Python PyBind. Okay, I don't understand. It works like PyBind or 11 or boost.python, that basically you need to write couple of lines of code for each of the methods that you want to provide to C++. Thanks to this package called Rapid, which is developed by Philippe Gras, makes use of the LLVM to understand the C++ classes and generate these 3 or 4 lines of code per method automatically. So that really helps a lot on producing that, and it also helps a lot on the sustainability in the long term, because new versions of JAM4 will be happening basically every 6 months or 1 year. So it's nice to have a mechanism by which you can incorporate the changes in a less effort manner. So the basic, once you have done that, the basic interface is quite straightforward. It looks like a Julia thing, or you just say using JAM4, you just instantiate the objects that you want there. For the people that are not used to Julia, it makes a bit different that you don't have methods of function. The method does not exist. You have to pass the object as the first argument into the function, but that's really you learn very quickly. All the classes of JAM4 are prefixed by G4, which makes very nice because you can export all of them. There is no conflicts with other types that will be fine, or very likely not many conflicts. So you can just use it and so on and so forth. Okay, that's quite straightforward. What concerns the package structure, what we have achieved here is that the JAM4 package is really a purely Julia package. And everything that has to do with the binary code, this is done in _GLL packages, which has been produced with the binary builder. And then all the different artifacts for the different architectures and platforms has been available there, and then automatically, transparently by the user, they are loaded. So that's really great. It works very easily from the basic flavors, Linux, Mac OS, and Windows, which certainly is an advantage. It's an advantage really for people that wants to use this toolkit, and they just do a package add, and that they get everything that it requires. Compared to if you want to use the same thing in C++, it's a quite heavy operation. Okay, you have to build it yourself because typically the binaries that are available are not exactly what you need to your platform. basically, the way this is done in the C++, user has to inherit from a base class, which then you declare it, which then the framework, the toolkit will call you, okay? But in Julia, you don't have inheritance, you don't have methods, you don't have this thing. So what I do simply is to provide functions there. And to provide functions like is shown here, that, I don't see my mouse, but okay. You provide functions like in this case, a step action that you will provide some structure on the JM4 toolkit, which represent a step, and you provide some reference onto something that from where you can get all the rest of information, okay? Something like represents the full application. And then in here, you just extract the information you want. On that step, what was the energy that I got? What is the position of this step? What is the next? Which is the direction, and so on and so forth. Whatever you want to extract, you can have it there. Now, multi-threading, I mentioned that JM4 provides multi-threading in there, that it is able to process each collision or each event in parallel. So that's it's a trivial parallelization, because each event or each set of particles are independent, so you can really develop that in parallel, and it has a very, very good scaling. Thanks to the threads are managed by the toolkit, but thanks to the foreign thread adoption that was introduced in 1.11, this is now possible that the threads are in JM4, but these are calling functions from Julia, okay? So that works nicely. The only detail you have to make sure is that each of these user actions are being called by several threads. So you have to worry about data races there, okay? So basically the trick here is that you duplicate the storage of the data that you have there, and each thread will be filling his own set of data, and then you merge at the end. You do the reduction. So user actions I mentioned already. It's nothing special. It's just Julia functions that get some from the arguments. You get the information you want. There is no globals, okay? And there is a way to get your own copy of the data that you want to fill with counters or histograms or you name it, okay? With some data frames or if you want to collect information. So that's typically for each application, you define what I call the simulation data, which will be the result of my application. The result of my application typically will be counters, some vectors of information, or some histograms, or some data frame, or something like that, and then you provide a reduce function to add all of them at the end of the run. And finally, you put all these things together, okay? You put all these things together in what is a G4GL application, where you put the detector geometry description, you put what physics you want, you put what is your particle generator, initial particle generator, how many threads you want to run, what are my actions, and basically you create an instance of that thing, you configure, you initialize, and you run. And then you can extract the information out of the thing. So nice. Once you have it in Julia, then you can also start using the bits and pieces of the Julia ecosystem there. And in that particular case, it was very easy to visualize the geometry and visualize the particles that you are producing on this during the simulation using, for instance, Mackie, including Boolean solids with this IGL package that is able to combine shapes and make Boolean operations with them. And at the same time, you have very interactive things in there. So how it will look like a full example in there, a full application is something that will take 100 100 lines long. Okay, it's nothing really exceptional. You define you define your simulation data, you define your geometry, and basically you put you combine together and you make one of these instances of this application with everything. Okay, basically, as I said, with what data I have, what the number of threads, the physics, the actions, and so on and so forth. And then in the same application, you can then use data visualization tools or analysis tools, and you can collect. And this is certainly an advantage with respect to the JAM4 in C++, which is combining other things on C++ is possible, but is not easy. Okay, that to do the simulation and at the same time the data I have collected to do some analysis with it and some visualization of it. Like in this example I'm doing, this is like a sampling calorimeter that you shoot some particles, and then you see the energy deposition in each of the layers of this calorimeter. So, and with Julia, as I mentioned, also it comes interactivity for free, which is great. It's great for developing your applications. You can develop your user actions and see what if you are doing correctly. And you with a revise module, you can change things. You can see what's going on. The same thing with notebooks. You can represent. You can see the geometry. You can see your detector. You can see how you are building up the detector, and visually you check that it makes really sense, and you didn't inverted the transformation and things don't fit anymore, and so on and so forth. And at the end, okay, everything is very well integrated on VS Code, on IDEs in there, which is great. Now you could ask yourself, what is the performance? Are we losing anything on doing that? And the answer is no. Obviously, the main number crunching is still in C++. The only thing that you offer is a Julia interface to the C++. So the performance should be equivalent to the C++ application. And in reality, it is like this, okay? If you run exactly the same example in the JAM4 toolkit, there is some basic example number 2. You can run it in both cases, and you can see that you get basically the same, except that the Julia is slightly longer on a startup, okay? But we know about that. And if you run it for one event, one takes less than a second to initialize and to produce one event, while the Julia case, it takes 6 seconds. But okay, since you typically run for hundreds, thousands, millions of events, because what you want is to really have high statistics, at the end of the day, you see the same performance. And then when you apply some multi-threading in there, you get the same scaling, because at the end of the day, the threads are running on the C++ pool, okay, of threads. Conclusions of this work. I mean, this package, the jam4.gl, allows people to develop simulation applications without the need to program in C++. The installation and the portability among the different major platforms is trivial. It really is very straightforward. You get a much higher level and friendly, at least this is what I think, a friendly user API. I mean, just counting the number of lines is you divide by 10 the number of lines that you have to write typically on a small application. And also you have a very nice built-in tooling and ecosystem which is very complete, and you can really exploit that. And the capabilities and the performance, it will be identical to the C++, because at the end of the day, as I said, you just call the C++. It's nothing special. We are not changing any physics model or anything here, okay? And the same capabilities, you will have it in one side and the other. And at the end of the day, is also, even if this evaluation, I think the conclusion is very positive, depending on where we go later in the physics, on the high energy physics, okay? And but nevertheless, this is a good add-on to the JAM4 project itself, because it provides yet another set of bindings on a language that will allow you to be very productive and without the need of learning C++. That for our domain on high energy physics is not a problem because most of the people working in our field know C++, but in other domains like medical physics and things like that, this is not as easy, okay, typically. And then it comes with the rest of the ecosystem on Julia, which it could be very nice for visualization, data analysis, and so on and so forth. The thing is, in a working state, and functionality can be added because I didn't wrap all the 2,000 classes that are in JM4. I only wrap the ones that you interact with it. But okay, it could be that for certain cases you need to interact with other classes, and then it's very easy. You just turn the handle and can be added. If you want to try out, there is a number. A set of Jupyter notebooks as a tutorial, which tells you step by step how to build a full simulation application, and includes a number of complete examples in there, which is quite nice. And then I finish with a bit of an announcement. We at CERN, we are organizing a Julia HEP workshop at the end of September, October, beginning of October. Which, okay, you are most welcome to participate if you wish.
Thank you very much. Any questions? Okay, we have one there.
The latency difference that you showed between the C++ and Julia can be reduced by precompiling the workload in the Julia package?
Probably, yes, probably, yeah. But I didn't worry. I was not worried too much. Okay, it's a few seconds. Taking into account that there are, I think it's written somewhere. I think I did more than 200 classes with the methods. I think, yeah, I'm wrapping almost 3,000 methods. Okay, which is quite a lot. And of course, you don't use the 3,000 methods, but since this is automatic, you say, I want to wrap this class, and this class comes with 20, you just wrap the 20, okay? It's done. But you see, there is a lot of things, and it really doesn't take very long to load, okay? And in addition, understanding that there is all these binary packages behind that it has also to be activated.
Thanks.
I have a kind of a comment. I think from the advertisement point of view, the example to benchmark on would be nicer to have also the next layer, the visualization or some sort of data analysis, and then you could compare the efficiency of the whole system, like not just a wrapper, because this is what you are showing, but also, for example, if I use a Python wrapper to Giant4, how long it takes to run the simulation, analyze the data, and make a plot. So then there would be some differences, more visible, I would say, from one to another.
Yeah. Concerning the Python, there is a Python wrap bindings for Giant4, but at the end of the day, they are not useful. Not useful because if you write your user actions in Python, and this is called every step for every particle, the overhead is terrible. Okay, you can do perhaps simple things, but if you want to do some more complicated thing on the user actions, it's completely useless. It's impractical. Okay? It's practical for the configuration part and all that, but it's impractical to run a big simulation with that. Now, and also for visualization and yes, Giant4 comes with some predefined visualization, but here you are much flexible, okay? Because the visualization is so simple with these interfaces to Mackie and things like that. You can say, look, I don't want that to draw these things in this way. I want to draw it differently, okay? And then it becomes trivial. For instance, I did this example here, like represents a bubble chamber, and I said I want to show the particles. I want also to put the labels, okay? I mean, GM4 doesn't do that, put the label, but to put the labels there was one line that I had to change, okay? So it gives you much more flexibility than what you have currently on the current system, because it's trivial. But okay, you can do something like that, okay? But at the end of the day, this visualization, you don't run big productions with a visualization on. This is basically to debug your application, okay? You want to make sure that the geometry is what you think, and you want to make sure that the physics you are showing there is what you think, okay? And then once you have it, you switch off visualization and you run for 1,000,000.
Thank you very much. Do we have other questions?
If I want to learn, if I want to learn Gen4 now without prior knowledge, is it possible to do that with this package? Or?
Yeah.
Ah, nice.
Yeah, of course. The details, the details of what each model does and what physics behind and things like that. There is pointers to the original C++ documentation, okay? But yes, you can, if you follow the tutorial, there are pointers there that will show you the really, if you want to interested in the details of each of the models, basically.
Okay, thank you very much. First question.
Yeah, very short question. If you're updating something like major on the C++ side, like you add a whole new feature, is there not a lot of maintenance then to also?
No, because
you use Rapid?
Yeah, because I use Rapid. You will have to, basically the input to this tool Rapid is basically a list of header files, and then all the classes that are found in these header files will be automatically wrapped. So if you are adding a new physics model with different, yes, you will have to add one line onto this input, and then you generate the thing, and then you can use it. Okay, modulo, yes, but it's trivial in the sense that it doesn't require a lot of coding. Okay, it's only to configure this input and to regenerate the wrapper.
Okay, thank you very much. Let's thank again Peremato. And we will have a 5 minutes break. Let's try to be here at 3:40 for the presentation of Jonathan. Thank you. Yes, you can.
Thanks for taking over. No problem. I got pulled into something else.
I like. I can continue if you want.
What next?
Yes, so we take 5 minutes break. Yeah. No plan. But, we will start in 4 minutes.
Oh, okay. Oh, okay. In frame. Okay.
I think the frame is, yeah, so this is the best place to keep the frame. So this is the center, but you can go from here to here about.
Okay. Right there.
That's good in frame? Yeah. So that's right in the center of the frame.
Okay.
Yeah, that's it. Yeah, okay. Thank you. All right. Enjoy the talks. Okay, we should get started. Thanks for coming for this final session of today. To start, we have a talk by Pablo Zubeta with Jonathan, and I think Pablo's here today, about lyotropic liquid crystals. I hope I said that right.
Yeah.
Yeah, over to you, Pablo. Thanks.
Okay. Thank you. So I'm Pablo. Jonathan couldn't be with us, but he's a PhD student and I'm a postdoc in the same group in the University of Chicago. And we work partly on studying liquid crystals. And I will be presenting the work we do and how we use Julia to study the systems. So first, what are liquid crystals? So liquid crystals are this like intermediate state of matter that behaves like a liquid, but still have some characteristics of crystalline solids. So if you can see, you have all of these elongated particles lying in the same axis, roughly, and this imposes interesting optical properties in the systems. So another class of liquid crystals is this so-called lyotropic liquid crystals, and in these properties of the system also depend on the concentration, and examples of these are abundant in biochemical systems, and in biology, like a school of fish could be thought of a sort of lyotropic liquid crystal, but also like the cells in the liver align themselves as a liquid crystal. And other systems that are interesting and where you also have energy coming in from the medium to produce movement is the systems of microtubules connected by these kinesin proteins that are like molecular motors that bend these long shapes of microtubules and produce these shapes. And these shapes have these topological defects that are classified on multiples of -1/2. And these annihilate them or can be created. And these are important to study the dynamics of these systems. And I will stop talking about biology because that's not exactly my field, but I will switch to describing how we simulate these systems. The way we do it is, instead of using this director field I was speaking of, we use this tensor property that allows us to recover the dynamics of these topological defects I was talking about. And we do this generally by solving this sort of equation, which is a very straightforward equation. But the issue with this is that for describing these systems that depend on the concentration, here the concentration doesn't appear anywhere. And we don't have really a framework to do so. And this is mainly the work, the PhD work of Jonathan. So he is developing this framework based on this generic framework for non-equilibrium thermodynamics. And this is kind of how the equations we have to solve look like. We have equations for the density, the concentration, the mass, the velocity fields, and the disorder parameter that describes the orientation of these particles. And we have to solve this. And this part here of the Navier-Stokes is the hydrodynamics. We solve this in a PDE fashion, but the rest of the equations we solve as ODEs. So I'm kind of describing here what's the strategy we follow. So we have a single array of a flat array of scalars, and we reinterpret this depending on the structs that describe either the order parameter or the concentrations on the different parts we have in these equations. And we switch back and forth between structs of arrays or arrays of structs, depending on what we need to do. And we try to use the method of lines package and the modeling toolkit at some point, but it's not designed to really handle the things that we need to do. So we had to implement our own finite differences operators, but with Julia and multiple dispatch, that's pretty easy. And with that, we then apply these operators and solve separately the hydrodynamic, as I said, where we use a Lattice-Boltzmann method with Trixie. At the time when we started working on this, the interface for Trixie for this wasn't really developed, but the Trixie guys are really phenomenal, and they kind of wrote the documentation for extending these custom semi-discretization strategies that allowed us to couple the ODE to the PDE, and then we solve this iteratively. So, and we have to do more structs of arrays and arrays of struct switching. But here's how our custom finite differences operators look like. It's just a one struct with a tag that basically tells us what's the type of operator, and we have this interface, which is pretty simple, and then we have a single in-place method for the product of the operators on any sort of array. And this is an example of how the stencil operator works for gradient, but you just change the definition based on your operator, but the applying the operator is exactly the same for all of them. So with that, we're able to test different cases. For instance, we can check the limit where we remove the hydrodynamics, and we only have dependency on the concentration and the vector field, and we are able to reproduce experimental results that study these chromoglycate particles. If we put these liquid crystals in a microfluidic channel, then we're also able to recover the correct dynamics in a uniform wet flow. Or if we make the system independent on the concentration, we are able to really capture the dynamics of these defects and how they annihilate. And lastly, if we put everything everywhere, solve all at once together, then we're able to really capture the dynamics of these microtubes I was talking about in the beginning. So finally, what we did is we took these combined PDEs and ODEs, and we were able to combine them together by using these Trixie semi-discretization strategies. And this allowed us to verify the theoretical framework that was developed by Jonathan and see that it really allows us to recover the correct dynamics of the lyotropic liquid crystals. We still need to test against more systems like 3D or multi-component mixtures, but these are very challenging systems. And one of the trickiest things for this is finding, like all of these equations have parameters for how the different particles interact with themselves, and we cannot measure this experimentally. So we don't know what parameters we have to throw in to solve these equations. So this really suggests a way of doing end-to-end differentiation of the whole set of equations, trying to find what's the values of the parameters that give us the correct experimental dynamics. And with that, I like to thank you, and I would like to thank our supervisors, and that's it.
Thank you, Pablo. We have time for one question, I think, if there is one. Yes, please take the mic.
Yeah, you mentioned transformations between AOS and SOAs. I wonder why it is necessary to do them.
It's in part because of the different equations we're trying to solve. Some of them only require the gradients of the vector fields or the scalar fields, but other require the Laplacian or the divergence of some of these. So we cannot handle everything uniformly in order to compute all the quantities we need. So that's why we kind of have to do this back and forth depending on what's the operators we need to use for each equation.
Thanks, Pablo. Round of applause. Yeah. Our next talk is by Golankin, and it's about efficient composable solver for non-equilibrium flows. And Go, you have 10 minutes after the microphone is fixed. Thank you. Over to you.
Hello, everyone. My name is Go Longqing, and I'm a doctoral student majoring in CFD in Peking University. And today my topic is about our CFD solver applicable to non-equilibrium flows, KTMR. It is now open source on GitHub, and we welcome you to explore it. And firstly, math time. Let's keep it light, and I won't go too deep. I'll just give a simple overview of the theory so everyone can better understand what we are doing and why. You may already be familiar with traditional CFD solvers solving the conservation variables of the Navier-Stokes equations. In contrast, kinetic methods solve the distribution function in Boltzmann equation, usually in its model equation. And a distribution function typically looks like this in velocity space. Despite appearing simpler and having fewer variables, the distribution function operates in a higher dimensional space, making it challenging to solve. Integrating the distribution function is the variables of interest in fluids. Discretizing the velocity space allows for direct numerical integration, which is one of the most popular methods called DVM. Because kinetic methods describe flow at the molecular level, they are more fundamental and universal, but computationally expensive. However, these calculations are well suited for parallel processing, especially on GPUs. And with more and more powerful GPUs available, we believe it is time to do it. So KTMR. Oops. What's wrong with it? Yeah. KTMR, in essence, it is a large-scale distributed adaptive kinetic CFD solver. Our expectations for it are primarily focused on three aspects. In terms of scale, it features distributed parallel capabilities and adaptability. The most noted feature is that we have achieved synchronous adaptability in velocity and physical space, which is really crucial for large-scale kinetic simulation. Additionally, it will leverage GPU's differentiable programming, machine learning, and other technologies to enhance solving efficiency. And you know, all of them are areas where Julia excels. And regarding automation, we use Cartesian grids managed by Quad or Octree, known for their advantage in automated generation. And the post-processing capabilities are also integrated. And for applicability, KTMR is based on kinetic methods, specifically supporting DVM. Certainly, we will also implement other fluxes based on kinetic methods, and to address the shortcomings of Cartesian grids in adapting to boundaries, we will introduce the newest immersed boundary method to accommodate a wider range of boundary types. What's wrong with this? But unfortunately, the development of the solver is still in its early stage due to my busy schedule over the past year. But the green sections highlight functionalities we have already implemented. Could you help me? Okay. Since the user interface is not ready yet, KTMR is temporarily unavailable in package, but it will come soon. Just stay tuned for updates. And this is an example of non-equilibrium flow often used as a benchmark, which is solved by KTMR. It involves a square cavity where the lid moves to the right, driving the flow of gas inside. While not the most ideal demonstration of adaptive meshing, you can still clearly see the changes in the grid. The left video represents velocity space within a single physical grid, where they evolve synchronously during the flow process. And simply put, regions with higher distribution function velocity space require denser grids. In some extreme cases, the distribution function may move here or there. And to maintain, without adaptability, to maintain computational accuracy, the entire velocity space requires grids as dense as those areas the most dense, and in steeper cases, even denser. And this is just within a single physical grid and in only 2 dimensions. Now you can imagine how terrifying the computational cost would be. Thus, adaptive refinement in velocity space is crucial, and the situation is just exactly the same in physical space. And for this case study, we increased the grid scale. Scale is still not large, but anyway, we tested the solver's strong scaling on this grid. The serial proportion accounted for only about 0.36%, and achieving an about 80% efficiency based on 128 cores. Given the grid scale, these results are quite satisfactory. Well, developing a distributed parallel tree structure program from scratch is quite daunting. And unfortunately, I couldn't find a suitable Julia package for this task. But thankfully, Julia has excellent interoperability with other languages, so I turned to Carsten's P-Forest, developed in C code. Personally, I find the rules for Julia's interaction with C somewhat complex, but once understood, the process becomes quite enjoyable. Roughly speaking, P-Forest primarily provides the topological information of the tree grid, while most data and computational process are handled by Julia. The efficiency of solving is minimally affected by the interaction between Julia and the C. It is worth noting that the tree grid for velocity space was independently designed by myself, which I'll discuss later. Another crucial consideration when handling C functions is that Julia data passed into C functions are not visible to the garbage collector. Without GC preserve, Julia data can be prematurely collected, potentially leading to segmentation fault errors, and your IEPO will crash immediately, which was quite confusing and became my biggest nightmare during early development. DVM is quite different compared to traditional methods. Due to each physical grid having its own velocity space, the main feature of DVM is its significantly larger data size compared to traditional CFD solvers. This implies more costly inter-process communication and stricter memory requirements. To address this, our strategy involves redundantly computing fluxes at interfaces between adjacent processes. Computing the interface once is much faster than communicating it. To provide a better understanding of the memory requirements of DVM, here are some figures. For the moderately sized 2D grid I mentioned earlier, storing the data requires about 70 gigabytes. Additionally, storing an extra double type per velocity space grid increased the data size by about 4 gigabytes, making it quite expensive. Therefore, we have streamlined the tree structure information of the velocity space as much as possible. This streamlined implementation benefits from the second characteristic of DVM. The functionalities used in the velocity space are very basic. They only need to establish correspondences with neighboring physical grid velocity spaces and locate their siblings to facilitate grid coarsening. The velocity space tree grid I designed ultimately only requires an 8 type level information combined with Z ordering to achieve the above functionalities efficiently. This is also aided by Julia's efficient optimization for loops. But interestingly, even after a full garbage collection, the program's memory usage is significantly larger than the data size. Why is it? Well, I found during the adaptive processes in velocity space, areas need to be resized. Therefore, Julia allocates additional buffers to accelerate this process. Given the substantial number of these areas, the size of these buffers can become burdensome. And currently, Julia does not seem to offer a good method to release this portion of memory. Perhaps the only option is to sacrifice efficiency and copy the data into areas of exact memory size after each adaptation. This is something we need to consider moving forward. Suggestions for improvement are really welcome. And that's all for my talk. Thanks for listening, and welcome to visit our repository.
Thank you. A round of applause for Go. I don't think we have time for any questions right now, but you can ask Go around when around in the conference. Thank you. Thanks a lot.
Thank you.
Can we have the next speaker up, please? Oops. That's so important. Thank you. Thank you. Great talk. Okay, welcome again, folks, for our final talk of this evening in this room. We have Graham Stewart from CERN talking about jet reconstruction in Julia. Over to you, Graham. You have 30 minutes with a warning at 25. Thank you.
Thanks very much. All right, so jet finding in Julia. So this is work
that I've done together with Philippe Gras and Attel, who've been helping with this, and I want to tell you about. I suppose this talk actually, it's a little bit about the algorithm that we've implemented, but it's also a little bit of a sort of journey of discovery of Julia, of how we started just investigating things and you know, looking at various aspects of performance and ergonomics, and came to some very positive conclusions about Julia as a result of that. So I didn't know how much people would know about high energy physics, so I thought it was probably worth a little reminder of what it is that we're doing, particularly the experimental program at CERN. So CERN is located on the French-Swiss border, close to Geneva, and our flagship accelerator is called the Large Hadron Collider. So you essentially start with a gas bottle full of protons, and then you spin these up through the accelerator complex, and they get faster and faster, and eventually they go into this ring here, which is the Large Hadron Collider, where they will collide at the 4 principal experiment sites. And they reach 14 TeV, the 2 proton beams, which is the highest energy that you can reach, at least in a human particle accelerator. Nature still does a bit better in some circumstances. At each of the experiments, you have a big detector. So the idea here is that you're wanting to crash these protons together, and this will allow you to probe and explore some of the, you know, very most fundamental forces in the nature of the universe. Our experimental program, of course, is very much based around Higgs physics, which was discovered over a decade ago, but we still don't understand all of the properties of the Higgs boson. And there are lots of very active experimental programs to probe dark matter and the matter-antimatter asymmetry. And then, of course, one is always on the lookout for something that you didn't expect at all. So, you know, what is the real unknown? So the LHC is providing 30 million collisions a second to the different experiments, and there's a very sophisticated trigger system which is going to select a small fraction of these for offline analysis, because we can't afford to store them all is one thing, and actually the vast majority of the collisions are physics that we already understand quite well, so it would be useless, in fact, to store all of these events. Okay, so talking about events, what do these actually look like? So this is an event display from the ATLAS experiment. The interesting bits of the collision, so the very high energy interactions that you get between the quarks and the gluons inside of the proton, in general, these decay almost instantly, okay? So, you know, you never have a chance to actually see a Higgs boson itself. You're only going to see what it breaks up into pretty much instantaneously. So this is a view of an event display from ATLAS. So you can kind of see in the middle here is actually where the beam collided. It then changed, it produced a Higgs boson, which decayed into 2 B mesons and some W boson, which then decayed into a muon and a neutrino as well. So because all we see is the mess, I mean, it always reminds me of my kids when they smash something up and you go into the room and you think, oh my God, what was that originally? And that's kind of what it's like. So you see the decay products, and from that you have to reassemble what was actually going on inside of the detector. Now, the bit which is interesting for this talk here are these things which are called jets, which are indicated by these cones. These cones are going to come back later on in the talk, and they've been reconstructed there, which is essentially a spray of high energy particles, and you want to try and understand what was the source of those particular particles. So jets, if you take a 2-dimensional view of a jet, they look a little bit like this. So you have some original high energy unstable particle that decays into different pieces. These pieces are the things that you actually detect inside of the detector. They interact with the detector material to produce more and more energy deposits and particles, so you get more and more children of the parent particles. These get captured in the piece of the detector that's called the calorimeter, and the goal is really to take all of these pieces and reconstruct what the parent particle properties actually were. So this is what jet reconstruction actually is. Okay, so how do we do this today and how might we do it tomorrow? So in high energy physics, our experiment software is based on C++ and Python. Each of the four big LHC experiments has about 6 million lines of code. As Perry already mentioned, it's probably in total 50 million lines of code that are used across the entire field. Perry told us quite a lot about the wrappers that he's done to the main simulation package, Xeon 4. And later today, Jerry will talk about reading the specific data formats that we use in high energy physics with Unroot. That's at 5 o'clock if you want to catch that one. So like I say, yeah, mostly C++ and Python today, but we want to be open to new opportunities like Julia. And it does happen, of course, when you think about it. Our field 25 years ago, everything was written in Fortran. Now almost nothing is left in Fortran, so change definitely does happen. And we wanted to try and evaluate different languages. This is a multi-dimensional thing because one is looking as well as the algorithmic performance, also about the language ergonomics for different implementations. So we were looking for something that we could try out Julia with. And we decided that jet finding was a good test case. It's a good algorithm to do because we didn't want it to be so simple that it doesn't add very much information beyond general metrics that one might have in micro benchmarks of Julia, where we know it performs rather well. But we also didn't want it to be so complicated that it would take absolutely ages to do the Julia implementation. So jet finding is a good example of why I would call this a Goldilocks algorithm. As I already explained, the goal here is to cluster calorimetry energy deposits into jets. Okay, and you can see an example of what the output of that looks like there. Here what is shown is actually each of the original energy deposits, and there they are colored according to the way that they have been aggregated into jets. So each of the colors represents a different jet that we've managed to reconstruct. Now, there's actually a very optimized C++ package, which is used ubiquitously inside of the field, which is called FastJet. It implements a number of different algorithms for jet clustering. At the LHC, certainly for primary narrow jets, anti-KT clustering is popularly used because it has these two properties of being infrared and collinear safe, which I'll explain a little bit more about in a moment. But let's just sort of run over the algorithm. What does it actually do? So you start the algorithm, you define essentially the size of the cone into which you wish to reconstruct jets. So 0.4, like I say, is typical, although there are some large radius jet studies that might use cones of 1 or 1.5. And then you have this bunch of particles. So you're then deciding, okay, I've got all this mess of particles here. How am I going to combine them into jets and build up the jets? So in this case, what you do is you measure the geometric distance between all the different pairs of jets, as long as it's less than r. So you're basically saying I will never join together two things which are further away than r. So you look at the geometric distance and you work out the closest neighbor for each of the clusters. But then you define a metric distance. So you don't just use the geometric distance to decide how you're going to do the recombination. You use a metric distance, which is also based on the transverse momentum of the particles. And if you use -1, you get anti-KT is the algorithm. What distinguishes that is essentially that you will favor merging to jets that have a high PT already. Okay. If you use 0, then you're using purely the geometric distance, which is the Cambridge-Aachen algorithm. And if you use +1, you're essentially favoring merging very small energy clusters at the beginning, which is the inclusive KT. Okay, so you work out that metric distance, you then pick the jet which has the lowest value of that Dij metric, and then you merge those two. And you just basically continue that until there's no more mergers that you can do. And it's a nice algorithm to try because this part here that you have of measuring for each of the particles can be parallelized. But at the end, you have this kind of serial step where you need to optimize to find the lowest Dij. Okay. When you actually do that, this is what it looks like. I've built this little animation so you can see, but I think you very much get the idea here that the things are being clustered into places where you already have a high amount of energy. So this is the actual reconstruction process as it proceeds. It's because you're reconstructing into high PT jets, it means that if you add an infinitesimal amount of energy to the event, it will only be added right at the very end. So it can only produce an infinitesimal perturbation to the final result, which is called infrared safe. It's also called collinear safe because if you take an energy deposition and you just split it into two, then those two pieces will tend to recombine immediately, and so you don't perturb as well the final result. So this is what you're aiming for. This is a very nice property of anti-KT jet reconstruction, which is why it's so popular. Okay, there are different strategies for doing this, and we looked at two different strategies for implementing the algorithm. The one is called N2 plane, which is just a basic strategy where you consider all of the active clusters at any particular point in time. So you just have a global pool and you're considering everything against everything. And then there's an optimized version for higher densities, which is called the tiled implementation. And here, the trick is, because I will never merge anything that are more than the distance r apart, I essentially divide my space into tiles of r size. And then if I'm at this point here, I'm considering a jet in the center of this circle, I only care about these 9 tiles, right? Because I can't possibly merge anything which is outside of that. So the tiled algorithm, of course, it involves quite a lot more bookkeeping. You've got to build up the tiles. You've got to work out which clusters are in each tile. But the idea then is to reduce the amount of work that you actually need to do. So it does, the basic algorithm does more calculations, but it's slightly more amenable to parallelization as well. So those are the two different strategies that we wanted to implement. Now, we actually looked at a number of implementations, and I'll give them here. So of course, our benchmark is this FastJet package, which I already mentioned, which is a very optimized C++ implementation. That was also kind of our reference in terms of the results. So if we get the same as FastJet does, then we know we did a good job. We thought, well, you know, Python is super popular, so why don't we at least just do a test of what things look like in Python? And we did one in pure Python. Of course, we didn't expect it to be fast, but we thought, you know, ergonomically, it's a good test to do to check that it looks quite good. And then a lot of my Python colleagues always say to me, yeah, but you know, of course, Python's slow, but you know, you use Numba, you use NumPy, you use all of these things, you can accelerate it, it will get just as fast. Okay, all right, I'm going to give it a go. I'm going to use Numba and NumPy and see if I can get things to work. So we as well as the Julia implementation as well, and we presented the results about a year ago, and these were the results that we got. So at that particular point in time, I think what's noticeable is that in Julia we got close to the performance of FastJet, but we didn't quite make it. We were still some 12% off. In the tiled algorithm. In the plane algorithm, Julia was a lot faster than FastJet, and the Python implementations disappointed. The pure Python, as expected, was really slow, although it was nice to work with. The accelerated Python, it was just really hard. You just could not cast the problem into the way that Numba and NumPy actually wanted it to be. So we were happy with the tiled result. Of course, we got close. We were delighted with the plane result. We were very excited about that. But it's recently turned out that actually FastJet's behavior at this working point is quite pathologically bad. So despite the fact that everyone is using it, it has really poor performance at this particular working point. If you widen the cone, it gets quite a lot faster, and then the advantage of the Julia implementation is quite a bit less. But what was the ergonomics experience like? So, you know, the performance was kind of as we expected. Certainly we got there with Julia and got to good performance, but what was it like to actually work with? Well, like a lot of high performance C++ code, FastJet is really C that masquerades as C++. It uses the kind of traditional layouts and structures that you would use in C. It's actually pretty well written code. You know, I've done quite a lot of C in my life. But of course, it introduces some difficult points as well. So you have pointers to pointers. It can be quite difficult to reason about the code in different places. It's quite difficult to work with user types in FastJet. So you tend to have to do EDM transitions yourself, or you need to use templating to compile against your particular user types. I mean, I think the ecosystem for C++, everybody knows it, so it's very old school, not so easy to use at all. For Python, the pure Python code is rather easy to use and reason about, so it was nice to work with, but it's horrendously slow. The Numba and NumPy accelerated code became very unwieldy as the problem needs to be cast into NumPy array layout, which is not so obvious for this. I was quite surprised. This was the first time I tried to use Numba, and Numba acceleration doesn't work for some very simple things like array index wrangling is not supported, so you have to rewrite the translation between linear indexes and Cartesian indexes, which was, yeah, kind of surprising. All of the way in which the algorithm works, there is some Python level logic even in the accelerated version, and that's why it ends up being slow, because it ends up being kind of killed off by having a loop inside of the Python layer. Julia, well, it was great actually overall, I would say. There were a few things that kind of stand out as, oh yeah, I love this as sort of first experience with the Julia language. The broadcast syntax is really great. This is the way that we make some compact arrays that we are going to use for doing calculations and distance measurements, but that was really easy to use. I think the optimization macros are so easy to apply. You know, it's not like switching on -03 in your C++ code. You can really go to the piece of code where it matters, and you can say, okay, I need to optimize this particular bit of code, so it was great. And a really super ecosystem for developing and supporting packages. So the debugger was excellent. You know, the fact that you have the plotting infrastructure there in the language, which is still fast, was really good. Profiling, basic physics types, it was great. It is fast, but of course I would say that the algorithm is still critical. I mean, it doesn't do magic, right? You still have to write a good algorithm and then let Julia take over from there. I wanted to point out some less good aspects. Probably these are to some extent due to my naivety when I started this, but there were a few places where I sort of was banging my head and discovered some, like, oh, I didn't expect that at all. So I was doing some code debugging and I left a debug macro in a hot loop, and God, that costs a lot actually, even when you're not in debug levels. So don't do that, I think, is the lesson that I learned. And then there was one weird place where I slightly refactored a piece of code, and in a branch which is not really taken actually, because it was just a check to avoid dividing by 0, I mistyped the name of a variable. So it was an undefined variable, and that killed the performance. I didn't get an error, but it killed the performance. So that was kind of like, oh shit, I really didn't expect that at all. Probably there are some static checkers that I could have used to catch that one, but I didn't know about them at the time. I have to say that ultimate optimization seems to be quite hard because of the way in which the entire algorithm works. It's not just like a spot. I'm you know, using I want to look at the LLVM code for just this piece of code. I'm trying to profile the entire algorithm. You get into Julia internals quite quickly. And I noticed that the JIT output can be sensitive to what I thought were quite minor code changes. And then I looked at my flame graph and I was like, oh, shit, this is completely different. I don't know what the hell this happened here. So yeah, I'm sure that you could work on that. Certainly we got it to a place where the performance was though very good. Some improvements, actually, after we initially presented the results, I realized that there was a very significant time in that serial step, finding the minimum DIJ. And of course, that's actually, although that's kind of serial, it's actually kind of amenable to parallelization as well, because you can use a divide and conquer approach. So I used the loop vectorization macro, and that sped things up enormously, surprisingly enormously, actually. It's about almost 4 times as fast to use that piece of code, which is there, over the normal built-in Julia findmin. So yeah, I really hope loop vectorization stays. Please don't get rid of it. It's going to make me very sad if it goes away. So this needs to still be there. Okay, where are we for the performance right now? So for the Julia jet finding, this is sort of pretty much what we would expect, that you can see that the tiled algorithm scales a lot better with the average cluster density. The plain algorithm doesn't scale so well, so you would tend to only use the plain algorithm at this very low density regime, where it is a bit faster than the tiled algorithm because it has these lower overheads. If you compare to FastJet for the plain algorithm, as I already said, you know, it's quite a surprise that FastJet has this quite pathological behavior for these small cone sizes with the plain algorithm. But even if you go to a wider cone where FastJet behaves a lot better, Julia is actually faster by about 20%. In the low density regime. At the higher density, you'd be using the tiled algorithm anyway. And then for the tiled algorithm, we're about 15% faster than FastJet for this tiled strategy due to the more optimal search for the minimum value of the distance metric. It would be nice to understand maybe in a little bit more detail why Julia is a bit slower than FastJet. I'm convinced that it could be as fast, but it's just not quite there. Anyway, I mean, in the end, I guess the conclusion is we have a very optimized C++ package, and we got as fast as that, and even a little bit faster in Julia without a terrible amount of effort, actually. So what's the current status? So based on the experience that we gained, we thought, okay, this is actually worthwhile. We should release this as a proper package in Julia. So the lesson here is that, yeah, it's one thing to write some decently performing code. It's quite another to release it as a piece of code that other people could actually use. So I spent quite some time doing cleaning up and writing documentation and making sure that people could actually use the package. I have to say that for writing documentation, Copilot was kind of amazing. You could just highlight the method and say, okay, document this. And it didn't get it right all the time, but kind of interesting. We have this p-value, which is this power. It kept thinking that must be momentum, because surely in physics, p always means momentum. No, it's not quite. But it certainly saves you a lot of time. You have to look at what it does, but it saves a lot, and you get nice comprehensive documentation. And then, you know, I think when you start to work on these things, what's nice is that maybe Julia's gathering a bit of momentum inside the field. So quite unexpectedly, we have a contribution for jet substructure, which is rather important, and tagging from some colleagues in CMS. And just before this workshop, I had contact from some people in Atlas that want to use it as well, so they're very keen. They particularly want the jet substructure. It's of definite interest for the FCC, so the potential future CERN collider that could be 100 kilometers and bigger than the LHC. Our colleagues in FCC actually do use a lot of analysis level jet reconstruction on the events. So there are a couple of slightly different algorithms that we want to implement, because the ones that we've implemented right now are more for PP collisions. That shouldn't be too much trouble at all. Okay, so we're coming to my conclusions. So I think jet finding was a really good example to try inside of Julia. The performance was, in the end, slightly better than FastJet, which is a very optimized package. So yay, that's pretty good. The ergonomics in Julia were a lot better. So even when we were doing the tiled implementation, the fact that we were able to do everything with just, you know, references and objects and not pointers leads to a lot better memory safety, and it was easier to reason about the linked list. It's much easier to profile and apply optimizations inside of macros, so we enjoyed that a lot. Overall, the tooling was a bit better. I mean, it takes you a bit of time to learn the tooling and the right pieces that you want to use, but once you get there, you're like, oh yeah, this is really nice. And it's much more flexible because of the dynamic nature of Julia. It's much more flexible for users of the package to use their own data types. So together with a few other colleagues, we have a sort of a beta version for Momentum base package, which Uwe wrote. And the intention is that we can then very easily support input particles in anything that supports the for Momentum base operations. So the package is now live in the registry and it's starting to pick up users. The core code is done, but there's quite a lot to add to get to the state of the art, particularly the substructure and the taggers, but they shouldn't be too difficult. And yeah, it was a good experience. And let me just finish by saying, as Perry did already, we hope that anyone that's interested in high energy physics might take the opportunity to visit CERN at the end of September, where we will have our second JuliaHep conference, which we look forward to a lot. Okay, thank you for your attention.
Thank you, Graham. Yeah. That was very interesting. It's always interesting to see, a large algorithm, non-trivial algorithm implemented and sort of showing that the microbenchmarks aren't that bad, and aren't that wrong. Mm-hmm. So that's very interesting. We have time for a couple of questions, I think. Is there one? Two? Perfect.
Three. Mm-hmm.
How would you compare the number of lines of the Julia implementation with the C++ implementation, or just the developmental time in general?
It's definitely less. I didn't do the count lines of code. FastJet has quite a lot of different bits and pieces in it, though, so just a naive counting of the lines of code wouldn't tell you properly how things were. But as I already illustrated, there are definitely places where Julia's syntax just makes things more compact, like the broadcast syntax, which is a little bit more involved in C++ if you want to do it. So I think it's less. My guess is that I don't know how long the FastJet developers took to develop, so it's hard to say, the development time overall. But I would say that Julia has definitely a more comfortable development experience. Yeah, it's probably faster to do it there.
Do you know the compiler which was used for FastJet?
Yeah.
So, for example, Intel is still ahead of GCC, even nowadays, I think. Background.
Yeah, so this was with GCC 11.4. I've compiled FastJet a number of times during the course of this development, and I don't see any major changes with the compiler. It's -02 actually as well. FastJet, for its sins, uses auto tools, which if there's anything that makes you feel like CMake isn't so bad, try using auto tools. It's truly awful. So yeah, it's you could try optimizing FastJet even a bit more. You might be able to squeeze a bit more out of it.
Any last question? Okay, there's one there.
Thank you for the talk. Have you tried integrating this into the rest of the Atlas codebase? And if so, how have you found integrating Julia with, say, C++ and Python?
Okay, no. At the moment, we haven't. I think there are some things that we need from Julia to be able to do that. I think realistically, if you were to try and get this into the Atlas code base, you really want a statically compiled library that doesn't bring along the Julia runtime. You just absolutely need that because you're having to fit it into what is already a massive C++ enterprise. So we have thought about how to do it. But at the moment, I think we need to wait and work on things like static compilation to make that realistic. So I think that one of the things, we're kind of targeting the analysis side of things where users are reading some final n-tupled products and then maybe wanting to do some reconstruction of the jets. at that point in time. And that's definitely would work for the FCC, where FCC-EE is right now.
Thank you very much. I will bother you outside with other stuff.
Sure.
Only one comment I would like to make on the table you saw with the numbers where Julia was slightly slower than the FastJet. Actually, we had a similar item because we also compared C++ code with Julia code. And it is somehow strange that at some point it is initially C++ is faster, which seems like that the implementation of C++ is good. And then as the data goes bigger, the Julia goes extremely faster. And then the even higher, you have something going together, but Julia seems to go slightly slower. So we had the similar behavior in a completely different item. Yeah, thank you very much for the nice presentation.
Yeah.
Okay, thank you, Graham. Round of applause for Graham. Thanks. And that's it for this room for today, I think. Thank you, everyone, for coming. See you out there.
laptop.
Are we at time? Huh? It is 5. Okay. A minute. So let's give it a minute for any last minute entries. Okay, I think it's 5. Welcome once again to this talk by Ivan Utkin, who's from ETH Zurich, and he's talking about fastice.jl. Over to you.
All right, thank you for interaction. And yes, I'm going to talk about how do we model ice flow using GPUs and Julia. So we are a small team of researchers scattered across Switzerland, but yeah, so mostly it's done together with my colleagues. All of them are here today. So yeah, a little bit of motivation. So why do we want to develop the code to model ice flows using GPUs on massively parallels on supercomputers? There are actually other codes that do model ice flows, but so the target of our study, the ultimate goal is to be able to resolve things that are called ice streams. So here you see the map view of Antarctic ice sheet, and colors are velocities. And you can see, so these two white circles, they show what's called shelves, and on top of that you can see that this shelves are fed by this very kind of narrow structures that are called ice streams, and there the velocities of the ice surface, they reach kind of enormous values. So yeah, you can see there's a logarithmic scale, and in the kind of deep in the land and the ice sheets, the velocities are as low as several meters per year, and in this ice stream they reach velocities for up to 3 kilometers per year. And so this is important because this is how most of the ice gets discharged from the ice sheet into the ice, eventually contributes into the sea level rise. So understanding the dynamics of these ice streams is important. Right, so yeah, these ice streams, they are fast-flowing corridors of ice, and their formation mechanisms, actually it remains unclear. So we know that they are linked to certain mechanisms, and there are some ideas, but still there is no kind of universal model that's kind of would capture the formation, the onset and the shutdown of these ice streams, in a somewhat realistic geometry. And one of the problems is the problem is multi-scale, first of all, right? So the ice sheet has the characteristic size of thousands of kilometers, and the length of the ice stream is 100 kilometers, and the well, the shear margin, basically the kind of the narrow region where the strain rates are, well, the deformation is the highest. So this is the lowest scale that you need to resolve if you're trying to model this process numerically. It's few kilometers, and actually, well, if we start looking at the three-dimensional picture, then there could be some features that are like meters and tens of meters, and this problem is essentially three-dimensional. So to kind of capture adequately all the scales, we need to be able to resolve them well on across all this spatial and temporal scales. Right, so, well, there are some smaller examples that are kind of our toy models that we play with, and one example is this Vavilov ice cap, which is part of the Russian Arctic. And this is, well, the first case of ice stream-like formation in the modern data record. So usually with Antarctic and Greenland, we can only look at this ice stream, since they were there, well, since forever. And so we can only hypothesize what were the time scales and the dynamics and kind of the processes leading to the formation. And this small ice cap, so this is not an ice sheet, it's a much smaller object. And there the stable stream-like features, so this kind of corridor of ice that formed just over over the course of a few months, which well, also kind of sheds some light on the characteristic time scale that has to be resolved. So how do we handle this problem? We handle it with supercomputing. So yeah, we're kind of making it our goal to be able to handle all the scales, to capture this shear bands, so this narrow horizon of deformation. So yeah, so far kind of we managed to get some compute time on the largest supercomputer, which is powered by AMD GPUs, which is in contrast to well, all previous supercomputers that were well, harnessed in the NVIDIA GPU. So there were some kind of novel aspects that had to be well, handled. So fastice.gl, it's well, it's a library, it's a package, and this is our ice flow model that we develop, and it solves what is called thermomechanically coupled Stokes equations. So you might have heard about Navier-Stokes, so which are, well, the system of equations that models the fluid, the dynamics of the fluid, and Stokes is actually the same as Navier-Stokes, but without some, well, inertia, basically, so neglecting the inertial effects. But yeah, we have this thermomechanically coupled, which thermomechanically means that temperature variations and the interactions between mechanics and energy balance are important, yeah, because when the ice deforms, it heats up, so by kind of friction, and this in turn lowers the viscosity, which kind of leads to some interesting feedback. One of them is, well, can be believed to be linked to the formation of these ice streams. So we need to solve it over irregular geometries to be able to study real objects. So all the algorithms are fully GPU accelerated. So, well, we use kernel abstractions.gl. So everything is actually backend abstracted, including GPUs. So, and not only the well, the kernels, but the algorithms themselves, they have to be carefully optimized and designed to fully utilize the power of GPUs. So which means that they have to be optimized for memory throughput and, well, and some other things like locality of the access. So we try to avoid random memory access. And we try to minimize the extra memory needed for the solution as much as possible. So yeah, we use conservative finite difference discretization on regular Cartesian grids, because this is the simplest way to, well, tick all the boxes that we need. Yeah, so we need conservative methods because we have sharp gradients of the fields, including temperature. So, and if the method is not conservative, like for example the standard continuous Galerkin finite elements, then there can be kind of some significant effects like loss of energy. And finite difference discretization, it's something that is very simple to implement on GPUs, and by default it will already give decent performance. Yeah, so if the grids are regular, that means that we don't need to store any kind of distributed structures. We can implicitly treat the parallelization and the implementation. So yeah, instead we have to handle geometry, irregular geometry, and we do it with what is called immersed boundary method. So yeah, and this the solver, just kind of to advertise the bit, is part of the project that is called GPU for Geo. It was recently finished but extended for 1 year, and yeah, the goal of the project is to develop some novel GPU multiphysics solvers. So yeah, here there's there's an example of localization. Yeah, here this thing, it plays now. It will kind of slowly accelerate over time. So here you can see some artificial geometry. So what happens over time is that the flow, so this line kind of arrows, they show the velocity field, and the contours show the energy localization. And here on the right panel you can see the slice showing, I guess this is the temperature, so it shows that we have the localization and heating up of the the ice close to this bumpy rough features on the bedrock, so which is essentially what we try to resolve, but on a much larger scales. And the rest of the talk will be not about this, but about how we use Julia to implement all these things. So Fast Ice is, again, it's a library, so it's not a standalone, it's not a package, so it's not just an application that takes some configuration file and runs it. It is, tries to be Julia idiomatic, so it's a library where the configuration file is written as a Julia script itself. So it's structured like this. We have the Fast Ice library. It's just the solvers which implement the models. There are several of them. So isothermal, thermomechanically coupled. Well, also we have distinction between having this irregular geometry with immersed boundaries and not having, etc. So these are just the solvers. We have some tooling package. Well, right now, if you search for it, you won't find it. But it exists. And finally, we have the core package. So this bottom panel is the core package, which recently, so this was what I was doing kind of this year, mostly at some point we realized that all these foundations and something that kind of helps developing this grid-based finite difference code can be nicely packaged and help us to develop some other experimental codes in general. So now it's a standalone package that's called Schmid.gl. I will talk a little bit about it. And yeah, so it supports all these kind of things that make it possible to implement this model. So how do we handle grids? How do we handle, well, fields in mathematical sense, which can be discretized or continuous, differential operators, some interpolation, boundary conditions, distributed components, and some other things. So, well, some of that is a bit like transparent. That means that this is a work in progress, not implemented yet, but is being worked on. So the next part is, yeah, it's a little like the something that I'm excited about is the progression of the code. So how I was developing it over when we started, well, several years ago. It's just an example how this high-level abstractions in Julia help to develop more readable and easily maintainable code. For example, this is well, one of the functions that we need in our solver. This is a function that computes stresses. And to compute stresses, well, there is a mathematical notation. You might not understand what it means, or most likely you do to some extent, but so this is just the set of equations. And how do we write it in the code? Of course, we want it to be as close as possible to this notation because it's readable, and well, also it helps new people to join and to contribute meaningfully sooner. And yeah, the first version, it was, well, you don't have to read this. It's obviously that it's just spaghetti code. It's completely unreadable. I cannot read it. I wrote it. And yeah, this is when I realized that we have to introduce these high-level abstractions. There was a high, like the activational barrier to overcome because I was afraid that if I make this kind of easily accessible high-level abstractions. It might not work on GPU, or it might work but be much slower, and so on and so forth. But I gave it a try, and yeah, early 2024 we have a somewhat better representation. So you can already guess that some of these things, they somewhat closely resemble the math, but there were some things that I was not happy about, and so the most important part is this check bounce. We need to check. We've used several kernel updates together to better utilize well, caching and the shared memory of the GPU, so that we read as few as possible things from the memory at the same time. And this check bounce, well, first of all, they look ugly, and second, they make the things a little bit slower, and in some cases, even not a little bit, but quite significantly slower, well, because of some extra machinery that GPU packages needs to do to make possible this check and bounce and report on the errors and throw in an exception from GPU, etc. So I wanted to get rid of that, and yeah, so finally, now with this foundational library, chmi.gl, the same kernel looks like this. So you can just kind of map basically every mathematical operation to its counterpart. This is how we compute it, and yeah, it's not exactly the same, but it's much, much closer. You don't have, yeah, you just have some kind of partial derivatives, some interpolations, etc., but it's very close to math. And what is more important is that this abstraction comes for free. So Julia does a very, so when you tell it to inline something, it will inline something, and it does it much more well, willingly, that, for example, some other packages that yeah, refuse to do this, is no matter how hard you try, without some intrinsics, it's difficult to do. But in Julia, everything gets inlined and generates the same LLVM code, or, well, not LLVM probably, but the machine code is exactly the same as if you would write this spaghetti code by hand, which kind of makes me quite happy. So yeah, this is, it started originally as a core library for FastEyes. It's what it does is that it simplifies the development of algorithms on regular grid in general, and yeah, it provides some tools that yeah, help you to deal with grids, differential operators, some boundary conditions, etc. Important, so kind of a novel thing is that it's not just backend agnostic. Many things in Julia are now backend agnostic, but it's also dimensionality, so it fully kind of utilizes the multi-dimensional programming in Julia. So initially, API was heavily inspired by oceananigans.gl, which is a wonderful package. So yeah, kind of one of the reasons why I still decided to go with well, separate solution, because we have different needs. So we're also a CFD package, but not CFD in the same sense in oceananigans. So we, yeah, I decided that it was just easier to implement what we need in a separate package. So here you can see this code snippet, what it looks like to use some of the features. We can create a grid. Well, here in that case it's a uniform grid. It can be also non-uniform. We allocate some fields on a particular backend. In this case it's a CPU. We initialize these values, and then we can well, apply these boundary conditions. Also, yeah, so I won't discuss it in details, but there is this thing called batching. If we have multiple boundary conditions, they are batched together and sorted by dimension, by size, in, well, such a way that you only call one GPU kernel, so you don't, again, you don't pay for high-level abstractions in that case, at least. So yeah, the next thing that I wanted to show you quickly is the distributed part of FastEyes. Yeah, so we have algorithms that are very simple. We trade the algorithmic efficiency for well, basically very good scalability. We have much more iterations of our numerical code, so we recompute things redundantly all the time, and we have a lot of iterations, but instead all the operations are very local. And then it's very important to be able to hide the hides the communication, the computation, the communication behind computations. So what it means is that basically, if you look here on the right side, so unfortunately I don't see my mouse, but yeah, so this bottom panel with this green lines is basically the execution on the GPU of a kernel on a GPU. And what you can see is that when one, so this top long green line, when it ends, the next one immediately starts. So, and usually if you don't hide this latency of communication, there would be a huge gap that would be just GPUs idle, waiting for communications to the MPI to exchange things over the network. And the standard way to do this is to use what is called non-blocking communication and to decompose the domain into inner and outer parts, where the outer part finishes first because it has a lower volume, and the inner part is the bulk of the computation, so this is this upper line. But when the outer part finishes first, so these are these yeah, you can see these shorter green lines below the long green line. These are the outer parts, and when it finishes, we can immediately start MPI communication without waiting on the bulk of the data to finish computing. And this is only achievable because we have local iterative methods. And then, yeah, as you can see, we don't have any gaps, so the MPI manages to exchange everything that it needs to exchange, while this long green line executes. So now, yeah, the question is, how do you program this? And the usual way, so if you do it in C, usually you would just, this MPI, and in GPUs, they usually return you something that is called future promise, or some token that encapsulates the ongoing concurrent computation or communication, some I/O. And then you need to loop. So if you have many of these requests in MPI, if you know it, so this when you launch the receive and send, you get the request back, and then you need to loop over all of them to until the wait, and it also leads to spaghetti code. In Julia, recently all the packages, they started to more and more leverage this cooperative multitasking capabilities. So they map the ordering of operations to the built-in Julia cooperative tasks model, and currently all the GPU backends support this. And MPI to a certain extent also supports this. It's not maybe there's not enough syntactic sugar, but you can work around this. And yeah, the snippet on the right, instead of just looping over these requests, we spawn several tasks for things that should execute concurrently. And within each of these tasks, we just write the code as if it were a serial code. So we untangle this long spaghetti structure and write much better looking codes. And on top of that, it helps a lot with interaction between packages. So if you have several things going on, you call some libraries that also do some I/O, as long as it is non-blocking and implements this cooperative multitasking things, which basically means that it cannot block. It needs to always return the control to the Julia scheduler. Then you will have this nice interaction. So we thought that it was interesting to try this high-level thing to see if the Julia runtime is efficient enough to run things on, hundreds and thousands of GPUs. So one question that you might have is, high-level features are not for free. Of course, they're not. In many cases, so I was showing you before that some of the features come for free, which is a miracle somehow, but some of them are not actually for free. And when we first started playing with it, it was Julia 1.9, and we realized that if you just spawn a new task each time when you do the computation, which is very elegant and short code, but it leads to bad performance. So yeah, up the top panel is a CUDA-C implementation. This bluish lines, they come directly after one another. So this is the GPU execution and CUDA.gl. If you have this multitasking, then you see this nasty gaps that kind of that are comparable actually to the runtime of the of the code. So yeah, the takeaway is of course always profile your code. Thankfully, Julia gives us tools for that. So yeah, it means that making this API calls cooperative, it needs some caution. With Julia 1.10, the situation improved quite a lot because the garbage collector became so the actually the culprit why is that bad, because when you create a new tasks, it allocates quite some information, and when the task finishes, garbage collector starts doing bad things occasionally, and it leads to bad performance ultimately. So yeah, so here, thanks to Valentin Churavi, he in 10 minutes he drafted the codes, and then later for 1 month I was trying to understand how it works and make it work. So essentially what we did is we switched from this short and very local tasks to what is called long-running tasks. It's somehow a blend in between this the old approach where you loop over things and the task-based approach when you allocate something. So it works like it's a worker. It's a struct that is a worker. It has a channel that accepts work. It does the work, and then it notifies an event that the work is done. And then each worker gets its own local state. And basically, if we want to, some things to execute independently of one another, we just submit it to different workers. And then, for example, you have one worker, it's the left side of your computational domain. Another worker is the right side of computational domain, and you submit two things to them, and then they get executed cooperatively, so concurrently with one another. So for example, one can wait on the GPU computation while other is already started doing MPI. So it solves the issue of expensive finalizers almost. I will show you the benchmarks and you will see what's the almost part. So a couple of words about GPU performance. Kernels in FastEyes, they are memory bound. So we need to measure memory efficiency, how far we are from simply copying the memory around. We have, the metric, the standard metric for that is the effective memory throughput. We reach about like 60% of the theoretical, of the peak memory throughputs with a full Stokes simulation in both 2D and 3D. So, which is not 100%, so we still pay some price, but we kind of, for now, we live with that. So next thing, so one thing is the one GPU performance and the other thing is the weak scalability. How good we perform compared to just having things on one GPU. We decompose the domain statically. We use MPI for communication between processes, and we achieve about like 95% of parallel efficiency compared to one GPU, both on, so the left panel is SpeedSdyned, so NVIDIA GPUs, and right panel is Lumi, up to 512 nodes, and there we reach 96% of efficiency. Recently we managed to run the solver, the electromechanical 3D Stokes solver, on a full machine. So they give us 6 hours just to test stuff, and we run it at effective resolution of 18,000 cube grid points. And so we were surprised to see that if you enable garbage collector, then it's actually with Julia 1.9, it would drop to 0 very quickly. Or, not to 0, but like to 1%. And still, many recent improvements, it's actually not too bad. It goes like to 92%, but still having GC on during the benchmark still negatively impacts performance, which means that we cannot, for now, get rid of these long-running tasks and disabling GC and kind of some optimizations. So this is practically what I wanted to show, and here are some next steps. So we had this GPU4Geo project, which was about writing these solvers, and there is some ecosystem around it, including all this kind of packages. You might know some of them, including parallel stencil, implicit global grid, which is the kind of somehow the foundation of the thing. And well, Sam will, I guess, tell about it more in the future. And so what we submitted is the another project which is called DGPU4Geo, which is about, well, the same, but for the reverse modeling to compute sensitivities. So yeah, if any of you will be a reviewer on this project, please say yes. That's it. Thank you. Here are some links if you're interested in checking this out. Don't be surprised by very informative documentation. Just practically, not so good so far.
Thank you, Ivan. That was great. We have time for a couple of questions, I think. Yes. Let me start at the back here.
Thank you, man. Thank you for the presentation. I have a question, actually two questions. The first one is, can you tweak the finite difference order of accuracy? Like, I noticed that last year you guys were using parallel stencil, and in parallel stencil I think you only can use second order accuracy. Can you guys like use 8th order or 10th order? Can you guys tweak that, or is it hard-coded?
Yeah, so, well, so in parallel stencil, it's mostly the backend abstraction. There are macros for finite differences, but well, you can implement everything with any order, but you will not have this macros.
Yeah.
And this chmi.gl is well an attempt to provide some extra things just to compute these derivatives. For now, it's only a second order finite differences. The idea is that you can make this a parameter. The order of the approximation, but for now, and what we are using is the just the second order finite differences, which kind of, well, mostly because of locality of computation.
Can I ask another question? Yeah. And why did you guys decide to make a different implementation of the same, basically, principle from parallel stencil? Why did you guys switch to this new project?
Well, it's not a new. So it's so parallel stencil is backend abstraction, right? And this chmi, it has nothing to do with backend abstraction. So it's just the functions that you can call within parallel stencil, within kernel abstractions, or within your manual loops. So it's everything that is not about backend abstractions. It's just like derivatives and gradient and stuff like that.
Hi, thanks for your talk. I have a quick question. So the work that you're dealing with is usually mostly finite differences, but within this chmi package, like I'm working with finite volumes for surfaces, something similar. Would it then be able to pick parts of the chmi packages and work with finite volumes? So, like such an extension, would it make sense, or would it require like a complete rewrite?
Well, so kind of the main idea of chmi is to work with regular grids, and the finite difference that we use are conservative finite differences, which, well, they are just equivalent to finite volumes or one particular implementation of finite volumes. So, and we have functions like, well, compute flux on the interface, for example, which will compute something that is located in between two grid cells. So it can be a bit challenging to do anything that is not rectangular grids. I would kind of see that it will take a lot of effort. So yeah, we don't plan to have like general finite volumes on kind of unstructured or hexagonal or dual grids, etc. But in a sense, it is finite volumes because it's conservative. So
thank you.
There's a question there. I think that's the last one we will take.
Yeah, thanks a lot. It looks extremely exciting. My question would be, I mean, I arrived a bit late, so maybe you showed that at the beginning, but what's kind of the code that I would use as a user, for instance, let's say for the bumpy beds, or for, you know, how does it look like, the code to generate that result?
Yeah, that's a good question, because so we were mostly working on the internals. So the API that is exposed to user, for now, it has, well, some like blank spaces that need to be filled. I can show you what it looks like. So currently there are, well, you are responsible for setting up mostly everything using this chmi. package, and then you create a model within this fast ties, and then you just, well, you write your own time loop where you kind of then call this advanced time step function. In the future, when we understand how to better package it, we would do that. But yeah, this would also actually some feedback on how you would like to see that also would be kind of very welcome, because otherwise we do it only in a way how we would like to see it, and it would be cool if we can do it in a way that other people could use it as well. So.
Okay, thank you, Ivan. I think that's all the time we have for questions. There's a break, and in about 7 minutes' time, there's a keynote out in the field by Rachel Cookin and Michael Herbst, and that should be interesting. So see you all down there. Thank you. Thanks, Ivan.
Thank you.